Hello there and welcome back to the Science Sleepy Minds. Picture this. Right now, 1,000,000 miles from your pillow, a golden mirror the size of a backyard trampoline is floating in the permanent shadow of Earth, sipping on starlight older than anything your brain was ever designed to comprehend. It is not sleeping, it is staring. And tonight, you get to find out what it saw when it looked too deep, too far, and too clearly into the blackness between the stars. Fair warning, your comfortable little model of the universe probably won't survive this. The things the James Webb Space Telescope has pulled out of the dark are beautiful, yes, but they're also deeply, almost personally unsettling, because they suggest the cosmos does not care about our textbooks. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment with your city and local time. I love knowing that someone in Tokyo at 2 a.m. and someone in Dublin at midnight are drifting off to the same strange story. It makes the universe feel a little smaller, which is ironic given what we're about to discuss. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You need to go back to Christmas morning 2021. While most of the planet was unwrapping socks and pretending to be grateful, a European Ariane 5 rocket was sitting on a launch pad in Kourou, French Guiana, sweating in tropical humidity. Strapped inside its nose cone was the most expensive scientific instrument ever built, roughly $10 billion of folded mirrors, sun shields and career-ending anxiety for every engineer involved. The James Webb Space Telescope had been in development for so long that some of the scientists who proposed it in the late 1980s had already retired. A few had passed away. The running joke in the astrophysics community was that Webb's launch date was always 5 years from now, no matter what year you asked. Historians still argue whether the project survived more because of genuine scientific necessity, or because cancelling it would have been an even bigger political embarrassment than funding it. But on that December morning, the rocket finally lit. You can find the footage. You can watch hundreds of grown adults in mission control polo shirts weeping openly as the vehicle climbed through a pale blue sky and disappeared. What they were really crying about was not the launch itself. Rockets launch all the time. They were crying because the next month was going to be the most terrifying sequence of mechanical origami in the history of space exploration. See, Webb was too large to fit inside any existing rocket fairing in its operational shape. So the engineers did something bordering on theatrical hubris. They designed the telescope to fold up like a transformer toy, launch in a compact configuration, and then unfurl itself autonomously in the vacuum of space, with no possibility of a repair mission if a single latch failed. There were over 300 single points of failure. 300 moments where one stuck pin, one sluggish motor, one improperly tensioned cable would turn a $10 billion telescope into a $10 billion piece of space debris. NASA's official list of required deployments numbered 344. Every single one had to work. That is not engineering. That is a prayer written in titanium and Captain film. And here is your quirky little tidbit for the evening. The sun shield that unfurled to protect Webb's instruments from the sun's heat is about the size of a tennis court, but at its thinnest it is no thicker than a human hair. 5 layers of this impossibly delicate membrane had to peel apart in the cold of space without tearing, tangling, or sticking together. During ground testing, technicians discovered that the layers sometimes snagged on tiny fastener heads, so they actually added little strips of material they called flapper restraints, which sounds less like rocket science and more like something you would see in a medieval costume shop. The fact that these flappers work perfectly in space, at cryogenic temperatures with no human hands to coax them, is a small miracle most people never hear about. Over the following 2 weeks, you watched, well, the the whole world watched as each deployment step ticked off the list. The sun shield stretched taut. The secondary mirror swung into position on its tripod of slender booms, and then, in the moment that made optical engineers openly sob for the second time, the two side panels of the primary mirror folded into place and locked. 18 hexagonal segments of gold-coated beryllium, each the size of a coffee table, arranged themselves into a 6.5-meter dish of almost inconceivable precision. If you scaled Webb's mirror up to the size of the continental United States, the largest bump on its surface would be about 6 inches tall. That is how smooth it is. That is how obsessive these people were. By late January 2022, Webb had reached its destination, a point in space called the Second Lagrange Point, or L2, roughly 1.5 million kilometers from Earth. This is not an orbit around our planet. It is an orbit around the Sun that happens to keep the telescope perpetually in Earth's shadow, which means its instruments can cool to about minus 233 degrees Celsius, cold enough that the telescope's own heat does not drown out the feeble infrared whispers it was designed to collect. At L2, Webb is so far away that if you stood on its sun shield and looked back, Earth would be a tiny bright dot, smaller than you would be comfortable admitting. And then the engineers began the painstaking process of aligning those 18 mirror segments into a single, flawless surface. Each segment can be adjusted by motors that move in increments smaller than a wavelength of light. The first alignment images were predictably blurry, 18 separate smudges of a single star looking like a firefly convention on a foggy night. Over weeks, those smudges crept together, merged and sharpened into a single, blazing point. When the final alignment image was released, even people who do not care about telescopes caught their breath. It was a photograph of a random, unremarkable star, but around it, scattered like confetti, were hundreds of tiny smudges and spirals. Each smudge was a galaxy. They were photobombing the calibration shot. Webb had barely opened its eyes and already the universe was showing off. You're lying somewhere comfortable right now, and that is good, because from this point on the story gets heavier. The telescope worked. Against every odd, every budget hearing, every sarcastic headline about delays, it worked perfectly. And the moment it began its real observations, it started finding things that nobody was prepared for. The thing you need to understand about Hubble is that it was not just a telescope, it was a cultural monument. For over 30 years, the Hubble Space Telescope delivered images so gorgeous they ended up on dorm room posters, coffee mugs, and the lock screens of people who could not name a single constellation. Hubble showed you the pillars of creation, those towering columns of gas where stars are born, and it made you feel something. It made the universe look like art, and for a very long time that was enough. But science does not run on feelings. Science runs on data. And by the early 2000s, the data Hubble could deliver was hitting a wall. You see, Hubble operates primarily in visible and ultraviolet light, with a modest ability to peek into the near-infrared. That is fine for studying objects that are relatively close or relatively young. Galaxies in their prime, nebulae glowing with freshly ionized gas, supernovae caught mid-explosion. But when you want to see the oldest, most distant objects in the universe, visible light fails you. Here is why. The universe is expanding. It has been expanding since the Big Bang, and that expansion stretches the wavelength of light travelling through it. A photon that started its journey as bright ultraviolet billions of years ago gets pulled like taffy as space itself swells. By the time it reaches your telescope, that ultraviolet photon has been redshifted all the way down into the infrared. It is still carrying information, still humming with the story of whatever star or galaxy emitted it, but it has moved into a part of the spectrum that Hubble was never really built to see. Imagine trying to listen to a symphony through a wall. You can hear the bass line, maybe catch a muffled trumpet, but the detail is gone. That was Hubble's problem with the ancient universe. The music was there. The instrument just could not hear the right frequencies, and there was another obstacle, one that sounds almost poetic. Dust. The universe is full of it. Not the kind you wipe off a bookshelf. Cosmic dust. Tiny grains of carbon and silicate floating in vast clouds between the stars. Visible light bounces off these grains or gets absorbed entirely. Entire regions of star formation, the most interesting nurseries in the galaxy, are hidden behind curtains of dust so thick that Hubble saw nothing but dark smudges where spectacular activity was occurring. Infrared light, though, passes through dust the way your voice passes through a curtain. It barely notices the obstruction. So if you wanted to see the earliest galaxies, if you wanted to peer inside stellar nurseries, if you wanted to watch black holes feeding in the cores of distant quasars, you needed a telescope that spoke infrared fluently. You needed something Hubble could never become, no matter how many servicing missions you sent. That need was recognized surprisingly early. The concept that would eventually become Webb was first discussed in 1989, just 2 years after the proposal that led to Hubble's successor began circulating at the Space Telescope Science Institute. A workshop at that institute in 1995 formally recommended a large infrared optimized space telescope, and by 1996 the project had a tentative name: the Next Generation Space Telescope. It was later renamed after James Webb, NASA's administrator during the Apollo era, a choice that would eventually spark its own controversy, but that is a story for another night. What matters now is the engineering ambition. The scientists wanted a mirror at least 6 meters across, more than 2.5 times the diameter of Hubble's. They wanted it cold, absurdly cold, because infrared detectors are useless if the telescope itself is radiating heat. And they wanted it far from Earth, beyond the thermal pollution of our planet's own infrared glow. Every one of those requirements created a cascade of problems that took decades to solve. A mirror that large could not be made from a single piece of glass. So engineers at Ball Aerospace developed the segmented design you already heard about, 18 hexagons that unfold and align autonomously. The beryllium they chose for the mirror material is lightweight and holds its shape at cryogenic temperatures, but machining it into optical quality surfaces required inventing new fabrication techniques from scratch. Each mirror blank was shaved, polished, tested, shaved again, and polished again over a process that took years per segment. Then the segments were coated with a microscopically thin layer of gold, because gold is an excellent reflector of infrared light. That is why Webb looks the way it does in photographs. It is not painted gold for aesthetics. It is gold because physics demanded it, though you have to admit it does look spectacular. Here is a fact that tends to surprise people. Hubble orbits Earth at an altitude of roughly 540 kilometers. That is close enough that astronauts could visit it. They did, 5 times, performing increasingly daring repairs that kept the telescope running far beyond its planned lifespan. The most famous of those missions, in 1993, corrected a flaw in Hubble's primary mirror that had been causing blurry images since launch. A flaw, by the way, caused by a testing instrument that was assembled with one washer out of place. One washer, $1 billion mirror, ground to the wrong shape because of a piece of hardware you could buy at a corner shop. Historians still argue whether that servicing mission or the original flawed launch did more to shape public perception of NASA in the 1990s, because the rescue was so dramatic, it arguably made Hubble more beloved than a perfect launch ever could have. But Webb lives at L2, 1.5 million kilometers away. No shuttle can reach it. No astronaut is going to float over with a corrective lens and a wrench. If something breaks, it stays broken. That reality forced engineers to build redundancy into every system and test components, with a thoroughness that bordered on compulsive. Some subsystems were tested over 100 times before being approved for flight. The joke among Webb engineers was that the telescope had been tested so much it was probably tired before it ever left Earth. And yet there was one test they could never fully perform on the ground: the full deployment sequence in zero gravity. You can simulate weightlessness for individual components, but you cannot unfold a tennis court-sized sunshield in a vacuum chamber on Earth, while also mimicking the thermal environment of deep space. Some of it they simply had to trust. That trust was perhaps the most human element of the entire project. Thousands of people across 14 countries spent the better part of 3 decades pouring their expertise into a machine they would only get one chance to launch. No do-overs, no service calls, just a single Christmas morning rocket ride, and then a month of holding their breath while a golden origami flower tried to bloom in the void. The quirky footnote here is that Webb's project timeline outlasted multiple NASA administrators, 3 changes of the telescope's name, at least 2 serious cancellation attempts by Congress, and 1 pandemic. The fact that it launched at all is almost as remarkable as anything it has found. And what it found from the moment its instruments reached operating temperature was a universe that did not match the brochure. Hubble had given us a beautiful picture. Webb was about to tell us that the picture was incomplete, and in some places possibly wrong. The infrared eyes were open, the data was flowing, and the first deep field image was about to land on the desks of astronomers who thought they understood the early cosmos. They did not. You are about to find out why. The date was July 11th, 2022, and you could feel the anticipation even through a screen. President Biden, standing at the White House, was about to unveil the first full-colour image from the James Webb Space Telescope. The room was full of officials, scientists and cameras, and there was that specific hum of energy you get when people know they're about to see something that cannot be unseen. Biden, to his credit, seemed genuinely awestruck when the image appeared on the screen behind him. He said something about it representing a new window into the history of the universe. He was underselling it. The image was called the Webb First Deep Field, and it targeted a galaxy cluster known as SMACS 0723. Now that name sounds like a printer cartridge, but what it refers to is a massive collection of galaxies roughly 4 billion light-years away, sitting in a patch of the southern sky so small that if you held a single grain of sand at arm's length, that grain would cover the area of sky photographed. A grain of sand. That is how little real estate this image occupies. And yet what it contained was enough to make seasoned astrophysicists go very quiet for a very long time. The foreground of the image is dominated by the galaxy cluster itself. Bright, bloated elliptical galaxies and elegant spirals, their light warped and smeared by gravity into arcs and streaks. That warping is called gravitational lensing, and it happens because massive objects bend the fabric of space-time, which curves the path of light passing nearby. Einstein predicted this effect in his general theory of relativity, and Hubble had already shown us beautiful examples of it. But Webb's version was sharper, deeper, and far more information-rich. The lensing arcs in the SMACS image were not just pretty curves. Each one was a magnified portrait of a galaxy far behind the cluster, a galaxy so distant its light had been travelling for over 13 billion years. Webb was essentially using the cluster as a cosmic magnifying glass, borrowing gravity's trick to see things that would otherwise be too faint and too far to detect. And behind the cluster, scattered across every spare pixel of the image like confetti on a dark tablecloth, were galaxies. Thousands of them. Red ones, orange ones, tiny blue pinpricks, smudged spirals no bigger than a few pixels across. each one a collection of billions of stars, each star potentially hosting planets, each planet potentially holding oceans or atmospheres or, who knows, someone looking back. The sheer density of galaxies in that image was staggering. Hubble had taken its own deep field images, famously pointing at an apparently blank spot of sky for 10 consecutive days in 1995, and it found galaxies too. About 3,000 of them. Webb matched that depth in roughly 12.5 hours of exposure time. 12.5 hours versus 10 days. That ratio alone tells you how much more powerful the new telescope is. But the depth was not the most shocking part. The most shocking part was the colour of certain objects in the image. Some of the tiniest, faintest smudges were extremely red. In astronomy, red usually means far away, because of that redshift effect you heard about. Light stretched by the expansion of the universe. The redder the object, the more its light has been stretched, which means the longer it has been travelling, which means the older it is. Some of the red smudges in the SMACS deep field appeared to be among the most distant objects ever recorded. Their light had left them when the universe was barely a few 100 million years old, a cosmic infant still figuring out how to make stars. And yet there they were, glowing, structured, unmistakably galactic. That raised a question that would grow louder and more uncomfortable over the following months. How did those galaxies get so big so fast? You will get to that crisis in full soon, but for now, just sit with the image. Let it sink in. You're looking at a photograph that covers less sky than a grain of sand, and it contains more galaxies than you will meet people in your lifetime. Some of those galaxies are so far away that the light hitting Webb's detectors started its journey when the universe had not yet celebrated its billionth birthday. And between those galaxies, in the spaces that look empty, there are almost certainly more galaxies still, ones too faint even for Webb to see. The universe is not mostly empty. It is mostly full of things we have not built the instruments to detect yet. Here's a historical footnote that adds a layer of poignancy to this moment. When Galileo Galilei pointed his crude telescope at the Milky Way in 1610, he discovered that the hazy band of light was actually composed of countless individual stars. That revelation was so unsettling to the prevailing worldview that it contributed to his eventual conflict with the Catholic Church. 4 centuries later, Webb did something analogous. It pointed at what appeared to be emptiness and showed us it was teeming with structure. Historians still argue whether Galileo's psychological experience of seeing those stars for the first time is meaningfully different from what a modern astronomer feels when a deep field image loads on their monitor. The awe might be the same. The scale has just gotten obscene. There is a quirky detail about the SMACS image that most coverage glossed over. One of the gravitational lensing arcs, a long thin streak of reddish light, was actually the same galaxy appearing multiple times. Gravity had bent its light along several different paths around the cluster, creating duplicate images of one object at slightly different points in its own history. You were looking at the same galaxy at different ages simultaneously in a single photograph. That is not just astronomy, that is time travel rendered in pixels, and it happened not because anyone planned it, but because the geometry of space-time around that cluster happened to align in just the right way. The universe, it turns out, is its own best special effects department. The public reaction was intense and immediate. The image went viral within minutes. News outlets ran it as a lead story. Social media lit up with a mixture of wonder and existential dread, which is the correct response to seeing visual proof that you are cosmically insignificant. Some people compared it to the famous Earthrise photograph taken by Apollo 8 astronauts in 1968, an image that reshaped humanity's sense of its own fragility. The SMACS deep field did something similar, but in reverse. Earthrise made the planet look small, The deep field made the universe look incomprehensibly vast. Both images ask the same question: what exactly do you think you are in the face of all this? NASA released 4 more images the following day, each targeting a different object and showcasing a different capability of the telescope. You'll hear about several of those as this story continues, but the deep field was the one that broke the seal. It was the moment when Webb stopped being an engineering project and became a discovery machine. The data behind that image, and the images that followed, would soon trigger a cascade of scientific papers, heated debates, retracted claims, and at least one full-blown crisis in theoretical cosmology. The telescope had opened its golden eye, and the universe, it seemed, had been waiting to confess a few secrets it had been keeping for 13 billion years. The confession started almost immediately, and they were not polite. Within weeks of the first data releases, astronomers around the world began publishing preprints, early unreviewed papers shared online, with titles that range from cautiously excited to barely concealed panic. The problem was simple to state and devastating in its implications. Webb was finding galaxies in the early universe that had no business being there. Not small, faint, tentative little smudges of a few million stars clumping together for the first time. No, these were massive, luminous, structurally mature galaxies sitting at redshifts so high they existed when the universe was barely 300 million years old. To put that in perspective, the universe is currently about 13.8 billion years old. 300 million years is roughly 2% of that total age. It is the cosmic equivalent of finding a fully grown oak tree in a forest that was planted yesterday. You need to understand why this is a problem, and to do that, you need a quick sketch of how galaxies are supposed to form. The standard model of cosmology, called lambda CDM, describes a universe that begins with the Big Bang, expands rapidly, cools down, and gradually builds structure from the bottom up. First, tiny fluctuations in the density of matter, quantum ripples frozen into the fabric of space during inflation, grow under gravity into small clumps. Those clumps merge into larger clumps. Dark matter, which outweighs visible matter by about 5 to 1, provides the gravitational scaffolding. Ordinary matter, hydrogen, helium, a whisper of lithium, falls into the dark matter wells and begins to condense. Eventually, gas clouds collapse under their own gravity, heat up, and ignite nuclear fusion. Stars are born. Groups of stars collect into small proto-galaxies. Those proto-galaxies merge over hundreds of millions of years into larger galaxies, which merge again into the grand spirals and ellipticals you see in Hubble posters. The whole process is hierarchical, incremental and slow. It is supposed to take time. Webb's early observations suggested that the universe did not get the memo. One of the first objects to cause a stir was a galaxy candidate designated GL-Z13. Identified in Webb's GLASS survey data, it appeared to sit at a redshift of roughly 13, placing it just 300 million years after the Big Bang. If confirmed, it would be among the most distant galaxies ever detected. But the real shock was not its distance, it was its brightness. GL-Z13 was far more luminous than models predicted for galaxies at that epoch. It was producing stars at a rate that the early universe supposedly could not support. The gas should not have cooled fast enough. The dark matter halos should not have grown large enough. The supply chains of cosmic construction, gravity, gas dynamics, radiative cooling, should not have delivered a galaxy that big, that bright, that soon. And GL-Z13 was not alone. A flood of similar candidates poured out of the data. Researchers using Webb's NIRCam instrument, the near-infrared camera responsible for those gorgeous deep-field images, identified galaxy after galaxy at extreme redshifts, that defied expectations. Some appeared to contain stellar masses equivalent to billions of suns. A few showed evidence of organized structure, disc-like shapes, possible spiral arms, features that were supposed to take billions of years of mergers and gravitational settling to develop. Finding them in the infant universe was like discovering a Roman aqueduct on a construction site where the foundation was poured that morning. The astronomical community reacted with a mixture of exhilaration and caution. Exhilaration because this was exactly the kind of revolutionary discovery Webb was designed to make. Caution because redshift estimates based on photometry, measuring an object's brightness through different filters, can be wrong. A dusty galaxy at moderate distance can mimic the colours of a pristine galaxy at extreme distance. Astronomers call these interlopers, and the history of high redshift astronomy is littered with candidates that turned out to be imposters. Historians still argue whether the initial wave of impossible galaxy headlines did more to advance public engagement with science or to erode trust when some candidates were later revised downward. The truth, as usual, was complicated. But here is the thing that kept the crisis alive. Even after spectroscopic follow-up, where Webb splits an object's light into a detailed spectrum and measures the redshift with much higher precision, many of the candidates held up. Jade's GSZ140, confirmed in mid-2024, sat at a redshift of 14.32, meaning its light was emitted when the universe was only about 290 million years old. That is not a photometric estimate, that is a spectroscopic confirmation, the gold standard in the field. And the galaxy was not a feeble little ember. It was extended, meaning it had physical size. It was bright in the ultraviolet, meaning it was forming stars vigorously. It contained evidence of oxygen, an element that can only be produced inside stars that have already lived and died, which means at least one generation of stars had already completed its entire life cycle before this galaxy's light was emitted. At 290 million years after the Big Bang. Let that sit with you for a moment. The quirky footnote here is that oxygen, the element you are breathing right now, did not exist in the early universe. The Big Bang produced hydrogen, helium, and a tiny amount of lithium. That is it. Every other element on the periodic table was forged inside stars through nuclear fusion, or created in the cataclysmic explosions when massive stars die. Astronomers call these heavier elements metals, which annoys chemists to no end because in astrophysical jargon, anything heavier than helium is a metal. Carbon is a metal. Oxygen is a metal. Neon, a noble gas that wants nothing to do with chemistry, is a metal. It is one of those disciplinary quirks that makes interdepartmental faculty meetings quietly hilarious. But the point is serious. Finding oxygen at redshift 14 means stars had already formed, burned through their fuel, exploded, scattered their guts into space, and enriched the surrounding gas with heavy elements, all within a few 100 million years. The cosmic kitchen was cooking at a pace nobody anticipated. Some theorists responded by tweaking existing models. Maybe star formation in the early universe was more efficient than assumed. Maybe the first stars were extraordinarily massive, burning through their fuel in just a couple of million years and seeding the cosmos with metals almost immediately. Maybe dark matter halos grew faster in certain overdense regions, giving galaxies a head start. These are reasonable adjustments, and some of them may well be correct. But others went further. A few papers suggested that the sheer abundance and mass of these early galaxies might require more fundamental revisions, changes to our understanding of dark matter, dark energy, or even the initial conditions of the universe itself. The whisper you kept hearing in seminar rooms and on astrophysics Twitter was a question nobody wanted to ask too loudly. What if lambda CDM, The model that has successfully described the large-scale universe for over 2 decades is missing something important. You're not going to get a clean answer to that question tonight. Nobody has one yet. But the galaxies are real, the data is solid, and the discomfort is productive, because discomfort in science usually means you are about to learn something new. The impossible galaxies of the early universe are Webb's first major provocation, and the telescope was just getting warmed up, or rather, cooled down. It operates at minus 233 degrees after all. The discomfort did not fade, it deepened. As more data flowed in from Webb's first and second observation cycles, the impossible galaxies multiplied like uninvited guests at a party that was already over capacity. Each new discovery landed with the same unsettling rhythm. An object too massive, too luminous, too structurally sophisticated for its age, confirmed at a redshift that placed it in an era when the universe should have been a formless soup of cooling gas and fledgling dark matter halos. And the theorists, bless them, kept trying to absorb the blows without abandoning the framework that had served cosmology so well for so long. But the framework was creaking. You should picture the situation the way a detective might. Lambda CDM is your prime suspect's alibi. It has checked out for decades. It predicted the cosmic microwave background radiation with exquisite accuracy. It explained the large-scale distribution of galaxies across the sky. It accounted for the observed ratios of hydrogen and helium produced in the Big Bang. It passed test after test with the smug confidence of a theory that knows it is right. But now a new witness has walked into the room, Webb, and the testimony does not match the alibi. Not catastrophically, not in a way that proves the alibi is fabricated, but in a way that makes you lean forward in your chair and start asking follow-up questions. One of the most talked about findings came from a team led by Ivo Labbé, who published a paper in early 2023 identifying 6 candidate galaxies at redshifts between 7 and 10 that appeared to have stellar masses rivaling or exceeding the Milky Way's. The Milky Way, your home galaxy, has had 13.8 billion years to assemble its roughly 200 billion stars. These candidates seem to have done comparable work in less than 700 million years. The paper's tone was measured, as scientific papers tend to be, but the implications were incendiary. If even one of those mass estimates held up, it would mean that either galaxies formed stars with an efficiency far beyond anything predicted, or that the models calculating how much mass can accumulate in a given dark matter halo by a given time were fundamentally miscalibrated. Neither option was comfortable. The response from the community was vigorous and sometimes sharp. Some researchers pointed out that stellar mass estimates from photometry can be unreliable. The way you estimate a galaxy's mass from Webb data involves fitting the observed brightness at different wavelengths to a theoretical template, a model of what a galaxy of a given mass, age and dust content should look like. But the templates assume certain things about how stars form and evolve, and those assumptions may not hold in the extreme conditions of the early universe. If the first generation of stars were significantly different from today's stars, more massive, hotter, with different chemical compositions, then the templates could overestimate the mass. You might think you're looking at a galaxy of 50 billion solar masses when you're actually looking at a smaller galaxy containing unusually bright stars that are fooling your models. This is a legitimate concern, and several early candidates were indeed revised downward after more careful analysis. But the revisions did not eliminate the problem. They softened it. Instead of finding galaxies 10 times more massive than expected, researchers found galaxies 3 to 5 times more massive than expected. That is less dramatic in the headlines, but still deeply problematic for the theory. A factor of 3 is not a rounding error. A factor of 3 means something in your model is wrong, even if you are not sure what. And then there were the shapes. Some of these early galaxies were not the irregular, blobby messes you would expect from objects still in the chaotic process of assembly. They had disks. They had what appeared to be ordered rotation. A few showed hints of bar structures, those elongated features you see in the centres of nearby barred spiral galaxies like our own Milky Way. Bar formation requires a galactic disk to be dynamically settled, meaning the stars and gas have been orbiting long enough to establish a stable pattern. In the local universe, bars are common in mature galaxies that have had billions of years to settle. Finding them at redshift 6 or 7, less than 1 billion years after the Big Bang, was like finding a perfectly organised bookshelf in a house that was still under construction. Historians still argue whether the photographic evidence of these early bars is strong enough to be conclusive, or whether the human brain's tendency to see patterns is doing some of the heavy lifting. The debate is ongoing, but the images are suggestive enough to keep people nervous. Here is the fringe tidbit that floats around the edges of this discussion, and you should treat it with appropriate skepticism. A small number of researchers, most notably Eric Lerner, have argued that the abundance of massive early galaxies is not just a challenge to lambda CDM, but evidence against the Big Bang model itself. Lerner has been a critic of Big Bang cosmology for decades, advocating instead for a non-expanding universe in which redshift is caused by mechanisms other than cosmic expansion. His views are firmly outside the mainstream, and the vast majority of cosmologists consider his alternative models to be inconsistent with the full body of evidence, particularly the cosmic microwave background and the observed abundances of light elements. But Webb's discoveries gave his arguments a brief moment in the spotlight, and a few viral articles with headlines like "Webb Telescope disproves the Big Bang" circulated widely in late 2022 and early 2023. Those headlines were misleading, as you will explore in more detail later, but they captured a genuine public anxiety. If the experts are surprised, how solid is the ground they are standing on? The honest answer is that the ground is solid but not immovable. Lambda CDM is not a house of cards that collapses if you pull one piece. It is more like a building that may need a new wing. The early galaxy crisis could be resolved by adjustments within the existing framework. More efficient star formation, different initial mass functions for the first stars, revised feedback models that allow gas to cool and collapse faster. Or it could require something more radical: new physics in the dark sector, modifications to the way dark matter behaves on small scales, or revisions to the inflationary model that sets the initial conditions for structure formation. What Webb has done is turn a theoretical possibility into an observational demand. Before Webb, you could argue about early galaxy formation using models and simulations. Now you have photographs, you have spectra, you have data points that sit stubbornly above the predicted curves on graph after graph, and data has a way of winning arguments that theory cannot settle. The telescope found galaxies that should not exist, and the universe has offered no apology. It simply expects you to update your understanding, which, if you think about it, is the most scientifically honest thing the cosmos has ever done. It showed you the evidence and left the interpretation to the humans, flawed models and all. You're drifting deeper into this story now, and the galaxies are only the beginning. Because Webb also looked at what powers those galaxies, and what it found at their centres was, if anything, even more disturbing. The stars came first, or at least they were supposed to. In the standard story of cosmic history, the universe spent its opening act in darkness. After the Big Bang, space was filled with a hot, dense plasma of particles and radiation, all tangled together in a glowing fog. About 380,000 years later, the universe cooled enough for electrons to combine with hydrogen and helium nuclei, forming neutral atoms. The fog cleared. Light was free to travel, but there were no stars yet to produce it, so the universe entered a period cosmologists call, with characteristic flair for the dramatic, the Dark Ages. No light sources, no galaxies, just vast, slowly cooling clouds of gas drifting through an expanding void, waiting for gravity to start the next chapter. The next chapter is called Cosmic Dawn, and it is one of the primary reasons Webb was built. This is the epoch when the first stars ignited, the first galaxies flickered to life, and the universe transitioned from a dark, neutral wasteland into the luminous, ionized web of structure you see today. The problem is that before Webb, almost everything we knew about cosmic dawn was theoretical. Hubble could see galaxies out to about redshift 11, maybe 12 on a very good day with gravitational lensing. But the earliest stars, the ones that lit the match, were expected to live and die at redshifts of 15, 20, maybe higher, far beyond Hubble's reach. There were ghosts in the equations, necessary to explain what came later, but never directly observed. Webb changed that, not by photographing individual first-generation stars, which are still too faint even for Webb's mirror, but by capturing the light of the earliest galaxies in enough detail to deduce what kinds of stars they contain. And the deductions were startling. The spectra of galaxies at redshifts above 10 showed signatures consistent with stellar populations that are extremely hot, extremely massive, and extremely short-lived. These are the population 3 stars, a hypothetical class of stars that have never been directly observed but have been predicted by theory for decades. Population 3 stars are supposed to be the firstborn, formed from pure hydrogen and helium with no heavier elements to help the gas cool efficiently. Without efficient cooling, the gas clouds that collapse to form these stars remain hotter and larger, producing stars that can be hundreds of times the mass of the Sun. Some models predict individual stars of 1,000 solar masses or more, blazing with a luminosity that would make our Sun look like a nightlight. These behemoths would have burned through their nuclear fuel in just a few million years, a cosmic blink, before dying in spectacular explosions. Some would have ended as supernovae, scattering their freshly forged heavy elements into the surrounding gas and seeding the next generation of stars with the carbon, oxygen and iron needed for planets, chemistry, and eventually you. Others, the most massive, might have collapsed directly into black holes without exploding at all, swallowing their own light in a final act of gravitational selfishness. Either way, they would have been brief, brilliant, and transformative. The universe before them was simple. The universe after them was complex. They were the bridge. Webb's observations of the earliest galaxies suggest that this bridge was crossed earlier than anyone expected. The presence of oxygen and other heavy elements at redshifts above 13, which you heard about in the impossible galaxies, implies that at least one full generation of stars had already lived and died by that point. If population 3 stars formed, burned, and exploded within the first 200 million years after the Big Bang, then star formation must have begun almost as soon as the Dark Ages ended, and possibly before they fully ended. Some models now suggest that pockets of gas in the densest regions of the universe could have started collapsing into stars as early as 50 million years after the Big Bang. 50 million years sounds like a long time when you're waiting for your dinner, but in cosmic terms it is almost instantaneous. Here is the quirky detail that makes this even more fascinating. The very first stars would have produced a specific kind of light signature, intense ultraviolet radiation with a sharp cut-off at certain wavelengths created by the helium in their atmospheres. This signature, if detected, would be a smoking gun for population 3 stars. Webb has been hunting for it, and while no definitive detection has been announced as of the latest data releases, several candidate signals have been identified in the spectra of very high redshift galaxies. One tantalizing hint came from a galaxy at redshift roughly 10, where the spectral shape suggested a contribution from extremely hot metal-free stars mixed in with a younger population of normal stars. It is not proof, but it is the closest anyone has ever come to catching a population 3 star in the act, even if that act ended 13 billion years ago. Historians still argue whether the concept of population 3 stars should be credited to a single originator, or whether it emerged gradually from the collective work of multiple theorists in the mid-20th century. The classification system itself, population 1, 2 and 3, was first proposed by Walter Baade in the 1940s based on observations of stars in the Milky Way, but the extension to a hypothetical first generation came later, as models of Big Bang nucleosynthesis made it clear that the earlier stars must have formed from primordial gas with no metals at all. The numbering is also counterintuitive and mildly infuriating. Population 1 stars are the youngest, like the Sun. Population 2 are older, metal-poor stars found in globular clusters in the galactic halo. Population 3, the oldest of all, were named last because they were predicted last. Astronomy, it seems, numbers things the way a sleep-deprived graduate student organises a filing cabinet, backwards and with no apology. What matters for your journey tonight is the implication. Webb is telling us that the cosmic dawn was not a slow, gentle brightening, like a sunrise on a lazy Saturday. It was more like someone kicking the lights on in a dark room. The first stars formed fast, lived hard, died young, and left the universe permanently altered. Their explosions enriched the gas. Their radiation began the long process of reionizing the neutral hydrogen that filled intergalactic space, and their remnants, neutron stars, black holes, expanding shells of hot gas, became the seeds around which the next generation of structure would grow. And it is those remnants, particularly the black holes, that lead you into the next and perhaps most unsettling chapter of Webb's discoveries. Because some of those black holes did not stay small, some of them grew to monstrous sizes in what appears to be an impossibly short time. And when Webb pointed its instruments at the hearts of the earliest galaxies, it found engines of destruction so powerful that they challenge not just our models of galaxy formation, but our understanding of gravity, matter, and the basic physics of how things grow. You're about to meet the monsters in the cradle. You've probably heard the term black hole enough times in your life that it has lost some of its menace. It shows up in science fiction, in pop songs, in motivational posters about letting go of negativity. But strip away the cultural familiarity and what you're left with is one of the most violent concepts in all of physics, a region of space-time where gravity is won so completely that nothing, not light, not information, not even the fabric of space itself can escape. The boundary around this region is called the event horizon, and crossing it is a one-way trip. Anything that falls in is gone, not hidden, not compressed. Gone in the sense that it can never communicate with the outside universe again. Black holes are not just objects, they are exits from observable reality. Now in the local universe, black holes come in different sizes. Stellar mass black holes, formed when massive stars collapse at the end of their lives, typically weigh between 5 and 50 times the mass of the Sun. They're relatively small, relatively common, and relatively well understood. At the other end of the scale are supermassive black holes, which sit at the centres of most large galaxies and weigh anywhere from 1 million to tens of billions of solar masses. The supermassive black hole at the centre of the Milky Way, called Sagittarius A star, clocks in at about 4 million solar masses. The one at the centre of the galaxy M87, famously photographed by the Event Horizon Telescope in 2019, is roughly 6.5 billion solar masses. These are established facts, well supported by decades of observation. What is not well understood is how supermassive black holes got so big. In the local universe, that is less of a problem, because they have had billions of years to grow. A black hole grows by accreting matter. Gas, dust, stars, anything that wanders too close gets pulled into an orbiting disk of superheated material that gradually spirals inward. This process is energetically spectacular. The accretion disk can glow brighter than the entire rest of the galaxy, producing what astronomers call an active galactic nucleus, or, in its most extreme form, a quasar. But accretion has a speed limit. As matter falls in and heats up, it produces radiation, and that radiation pushes back against the infalling gas. There is a theoretical maximum accretion rate, called the Eddington limit, where the outward radiation pressure exactly balances the inward gravitational pull. A black hole feeding at the Eddington limit can roughly double its mass every 40 to 50 million years. That is fast by human standards, but painfully slow by cosmic standards if you are trying to build a billion solar mass monster in less than a billion years. And that is exactly what Webb found. The telescope identified quasars and active galactic nuclei at redshifts above 7, 8, even 10. Time periods when the universe was less than a billion years old, in some cases less than 500 million years old. And the black holes powering those objects were enormous, not millions of solar masses, hundreds of millions. In some cases, preliminary estimates suggested masses approaching or exceeding a billion solar masses at redshift 10, when the universe was roughly 470 million years old. You can run the math on Eddington limited growth starting from a stellar mass seed of, say, 100 solar masses at the moment the first stars died. You cannot reach a billion solar masses in 470 million years. You just cannot. Not even if the black hole is feeding continuously, which is itself unlikely, because accretion is messy, episodic, and frequently disrupted by the very radiation it produces. So how did they get there? This is one of the most active and contentious questions in modern astrophysics, and Webb has made it urgent. Before Webb, supermassive black holes at high redshift were known primarily from ground-based quasar surveys, and they were rare enough that theorists could treat them as statistical outliers, extreme cases that might be explained by unusually favourable conditions. Webb revealed that they are not outliers, they are common. The early universe appears to be lousy with oversized black holes, and that abundance demands an explanation that goes beyond fine-tuning the parameters of the standard growth model. Several ideas are on the table. One is the direct collapse black hole scenario, which you should enjoy because it sounds like science fiction. In this model, a massive cloud of primordial gas, thousands or even millions of solar masses, collapses directly into a black hole without ever forming stars first. For this to work, the gas must avoid fragmenting into smaller clumps, which normally happens when the gas cools. If something suppresses cooling, say, a nearby galaxy blasting the cloud with intense ultraviolet radiation that destroys the molecular hydrogen needed for cooling, then the entire cloud can collapse monolithically into a single, enormous seed black hole of 10,000 to 100,000 solar masses. Starting from that seed, Eddington limited growth can plausibly reach a billion solar masses by redshift 7. It is elegant, it is physically motivated, and it has never been directly observed. Webb is looking. Another idea involves super Eddington accretion, the possibility that black holes can temporarily exceed the theoretical feeding limit. If the geometry of the accretion flow is right, radiation can escape along the poles while matter continues to fall in along the equator, effectively bypassing the radiation pressure bottleneck. Some simulations suggest that brief episodes of super Eddington accretion could dramatically accelerate growth, especially in the chaotic, gas-rich environments of the early universe. Historians still argue whether Arthur Eddington himself, who was famously skeptical of black holes, would have appreciated having his name attached to a limit that black holes might routinely violate. Here is the quirky detail for this stretch of the night. One of Webb's discoveries in 2023 was a peculiar object nicknamed the Little Red Dot. Actually, there were many little red dots, compact, extremely red sources scattered across Webb's deep field images that did not match any known category of galaxy or star. Some turned out to be heavily dust-obscured galaxies, but others showed spectral signatures consistent with active galactic nuclei buried inside surprisingly small host galaxies. The black holes in these objects appeared to be disproportionately massive compared to their galaxies, violating a well-established relationship observed in the local universe where black hole mass and galaxy mass track each other closely. In the nearby cosmos, the black hole is typically about 1,000th the mass of its host galaxy's central bulge. In some of Webb's little red dots, the ratio was wildly off. Black holes that were overweight relative to their surroundings, like an engine too big for the car it was installed in. This matters because it suggests that in the early universe, the chicken and egg relationship between black holes and galaxies may have been different. Maybe the black holes came first, and the galaxies grew around them. Maybe they co-evolved but at different rates. Maybe the processes that built the first galaxies and the first supermassive black holes were not sequential but simultaneous, tangled together in ways the current models do not capture. Webb has given you the puzzle pieces. The picture they form is still blurry, but one thing is clear. The monsters at the hearts of galaxies were born earlier, grew faster, and became more powerful than anyone predicted. And they are making theorists lose sleep, which is ironic given the purpose of this video. You're settling deeper into whatever surface is holding you right now, and that is good because the next thing Webb has been wrestling with is something you cannot see, cannot touch, and cannot even properly define: dark matter. The invisible scaffolding of the universe, the stuff that makes up roughly 27% of everything that exists, and yet has never been directly detected by any instrument in any laboratory on Earth. You know it is there because of what it does. It pulls on things, bends light, holds galaxies together that would otherwise fly apart given the amount of visible matter they contain. But what it actually is remains one of the most embarrassing open questions in physics. We have built the most sensitive detectors ever conceived, buried them in abandoned mines and under mountains of Italian granite, and listened for the faintest whisper of a dark matter particle interacting with normal matter. So far, silence. Webb cannot detect dark matter directly either. No telescope can, because dark matter does not emit, absorb, or reflect light. That is rather the whole problem. But Webb can map where dark matter is by studying its gravitational effects with unprecedented precision, and those maps are turning out to be both beautiful and troubling. The primary tool is gravitational lensing, which you encountered back in the SMAC's deep field image. When light from a distant galaxy passes near a massive foreground object, a galaxy cluster for instance, the gravitational field of that object warps space-time and bends the light's path. The result is a distorted, magnified, sometimes multiply-imaged version of the background galaxy. By carefully analysing the shapes and positions of these distorted images, astronomers can reconstruct the distribution of mass in the foreground cluster. And since most of that mass is dark matter, you end up with a map of the invisible. Hubble was already excellent at this game. The Hubble Frontier Fields program, which ran from 2013 to 2017, produced some of the most detailed dark matter maps ever made by imaging 6 massive galaxy clusters with extraordinary depth. Those maps broadly confirm the predictions of Lambda CDM. Dark matter formed large, diffuse halos centered on galaxy clusters, with substructure corresponding to individual galaxies within the cluster. The agreement between observation and simulation was encouraging. Dark matter, whatever it was, seemed to behave the way cold, collisionless particles were predicted to behave. It clumped on large scales, distributed itself smoothly on small scales, and generally followed the script. Webb's lensing observations are sharper, deeper, and more detailed than Hubble's, and some of what they reveal does not follow the script. Several studies using Webb data have found that the lensing effects in certain clusters are stronger than lambda CDM simulations predict. The arcs are too curved, the magnifications are too high, the implied concentration of mass in the cluster cores is greater than the models say it should be. This discrepancy is sometimes called the lensing is too strong problem, which is not a very catchy name but does capture the essential frustration. The universe, according to Webb, is bending light more aggressively than our best simulations can reproduce. One particularly striking example came from the galaxy cluster Abell 2744, sometimes nicknamed Pandora's cluster because of the chaotic evidence of multiple past collisions between smaller clusters. Webb's image of Abell 2744, released in early 2023, was one of the deepest views of the universe ever taken, revealing galaxies at redshifts above 10 behind a foreground cluster whose gravitational lensing was exquisitely detailed. When researchers modelled the mass distribution needed to produce the observed lensing pattern, they found more mass concentrated in the cluster's core than simulations of lambda CDM clusters typically produce. The dark matter was clumpier than expected, packed more tightly around the brightest cluster galaxies, and producing lensing magnifications that stretched the limits of what the standard model could accommodate. This does not mean dark matter is wrong. It might mean that the simulations need better resolution, more realistic treatments of the ordinary matter that interacts with dark matter through gravity, or updated assumptions about the merger history of specific clusters. Simulating a galaxy cluster from first principles is a ferociously complex computational task, and even the best simulations make simplifying assumptions that could affect the predicted mass distributions. But the tension is real, and it is showing up in multiple clusters, not just one anomalous case. When the same discrepancy appears repeatedly across different objects observed with different instruments, it starts to look less like a fluke and more like a clue. Historians still argue whether the dark matter problem is fundamentally an astrophysical question or a particle physics question, and that distinction matters because it determines who gets to claim the discovery when the answer finally arrives. Astrophysicists have been mapping dark matter's effects for nearly a century, starting with Fritz Zwicky's observations of galaxy clusters in the 1930s. Zwicky noticed that the galaxies in the Coma cluster were moving so fast that the cluster should have flown apart unless it contained far more mass than the visible galaxies could account for. He called this missing mass dunkel Materie, dark matter, and was largely ignored for decades because he was, by all accounts, a brilliant but extraordinarily difficult person who many colleagues preferred to avoid. The quirky footnote here is that Zwicky was also the first person to propose using galaxy clusters as gravitational lenses, a technique that Webb now employs routinely. He was right about almost everything and rewarded with almost nothing, which is either a cautionary tale about scientific politics or a motivational story about persistence, depending on your mood. The deeper concern raised by Webb's lensing data is about the nature of dark matter itself. Lambda CDM assumes that dark matter is cold, meaning the particles move slowly compared to light, and collisionless, meaning the particles do not interact with each other except through gravity. This model works beautifully on large scales, but on smaller scales, inside galaxies and in the cores of clusters, there have been persistent hints that the real universe has less concentrated dark matter cores than the simulations predict. This is called the core cusp problem, and it has been debated for over 2 decades. Webb's finding of overly concentrated cores in some clusters might seem to contradict this, and in a way it does, which makes things even more confusing. Some clusters have too much concentration, some have too little, and the pattern does not obviously match any single modification to the dark matter model. What all of this tells you is that dark matter is not a solved problem with a few loose ends. It is a mystery wearing a mask of familiarity. We have given it a name, assigned it a percentage of the cosmic budget, and built a phenomenally successful model around its gravitational behaviour, but we do not know what it is. We do not know how it was made, and now Webb is showing us that we may not even know precisely how it is distributed. The scaffolding is real. The blueprint, however, might need revision. And somewhere in the data Webb is collecting right now, there might be the clue that finally cracks the case, or there might be another surprise that makes the case even harder. With this telescope, you're learning to expect the latter. There is a number that has been giving cosmologists headaches for nearly a decade, and Webb just made the headache worse. It is called the Hubble constant, and despite its name, there is nothing constant about the controversy surrounding it. The Hubble constant, denoted h0, tells you how fast the universe is expanding right now. Specifically, it measures the rate at which distant galaxies are receding from us as a function of their distance. A higher value means the universe is expanding faster. A lower value means slower. Pinning down this number is one of the most important tasks in all of cosmology because it determines the size, the age, and the ultimate fate of the universe. Get h0 wrong and everything downstream, every distance measurement, every age estimate, every prediction about whether the cosmos will expand forever or eventually collapse, goes sideways. The problem is that 2 different methods of measuring h0 give 2 different answers, and they have stubbornly refused to agree for years. This disagreement is called the Hubble tension, and it is not a minor quibble. It is a genuine crack in the foundations of modern cosmology, and some very serious people think it might be pointing toward new physics. Here is how the 2 methods work in simplified terms. The first method is called the cosmic distance ladder. You start with objects whose distances you can measure directly, like certain pulsating stars called Cepheid variables, whose brightness fluctuates in a predictable pattern tied to their intrinsic luminosity. By comparing how bright a Cepheid appears to how bright it actually is, you can calculate its distance. You use Cepheids to calibrate the distances to nearby galaxies, and then you use those galaxies to calibrate the distances to more distant objects called Type 1, a supernovae, exploding white dwarf stars that all reach roughly the same peak brightness. By measuring how fast the galaxies hosting these supernovae are receding, you get a measurement of h0. This method, championed by Nobel laureate Adam Rees and his team, consistently produces a value of about 73 kilometers per second per megaparsec. The second method comes from the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. By studying the tiny temperature fluctuations in this radiation, measured with extraordinary precision by the European Space Agency's Planck satellite, cosmologists can build a detailed model of the early universe and then run it forward in time using the equations of lambda CDM to predict what the expansion rate should be today. This method gives a value of about 67.4 kilometers per second per megaparsec. The difference between 73 and 67.4 might not sound dramatic, but in the world of precision cosmology, it is enormous. Both measurements have been refined to the point where their error bars do not overlap. The probability that the discrepancy is due to random chance is less than 1 in a million, depending on whose statistical analysis you trust. Something is wrong. Either one of the measurement methods has an unidentified systematic error, or the standard model of cosmology is missing an ingredient. This is where Webb enters the story with all the subtlety of a sledgehammer wrapped in gold foil. One of the telescope's early science programs was specifically designed to address the Hubble tension by reobserving Cepheid variable stars in galaxies that are also hosts to Type 1a supernovae. The idea was straightforward. Hubble's measurements of Cepheids in crowded galactic fields might be contaminated by the light of neighbouring stars, a problem called crowding bias. If you cannot cleanly separate the Cepheid's light from the stars around it, your brightness measurement could be off, and your distance could be wrong. Webb's sharper infrared vision, the thinking went, would cut through the crowding and either confirm or correct Hubble's Cepheid distances. If the distances change significantly, the Hubble tension might dissolve. It did not dissolve. In early 2024, the results came in from Adam Rees's team, and they were emphatic. Webb's observations of Cepheids in the galaxy NGC 5584 and others showed that Hubble's photometry had been accurate. The crowding bias was real but small, not nearly large enough to account for the discrepancy. The distance ladder value of H0 held firm at roughly 73. The Planck value held firm at roughly 67, and the tension, far from being resolved, was now confirmed by an entirely independent instrument with superior capabilities. The universe was expanding faster than it should be, according to the model that described its infancy. Or the model was wrong, or both. Historians still argue whether the Hubble tension will eventually be remembered as one of the great clues that led to a revolution in physics, or as a cautionary tale about systematic errors in complex measurement chains. The precedent could go either way. In the early 20th century, a similar disagreement about the age of the universe, geological evidence suggested the Earth was billions of years old, while early estimates of the Hubble constant suggested the universe was younger than its own planet, was eventually resolved by the discovery that there were two different types of Cepheid variables, and astronomers had been confusing them. The resolution was a measurement correction, not new physics. Some researchers suspect the current tension will end the same way, with some subtle error in the distance ladder or the CMB analysis eventually being identified. But others are not so sure. The quirky and slightly unsettling detail here is that the Hubble tension is not the only tension in cosmology right now. There is also the S8 tension, a disagreement between the Planck CMB data and measurements of how clumpy matter is in the more recent universe. The CMB predicts more clumpiness than observations of galaxy clustering and gravitational lensing actually find. This second tension points in a direction consistent with the first. The universe is not evolving from its early state to its current state in quite the way lambda CDM predicts. When two independent tensions both suggest the same kind of problem, the odds that both are caused by unrelated systematic errors start to feel uncomfortable. Several exotic explanations have been proposed. Early dark energy, a brief burst of accelerated expansion in the first 100,000 years after the Big Bang, could reconcile the CMB prediction with the local measurement by altering the sound horizon, the characteristic scale imprinted on the CMB fluctuations. Interacting dark matter, models where dark matter particles scatter off neutrinos or other particles, could change the growth rate of structure and address the S8 tension simultaneously. Decaying dark matter, modified gravity, extra relativistic species in the early universe, the theoretical buffet is extensive and none of the options have been confirmed. What Webb has contributed is clarity, not an answer, but a sharpened question. By confirming the distance ladder measurement with an independent telescope, it has narrowed the space of possible explanations. The error, if there is one, is not in the Cepheid photometry. If you want to solve the Hubble tension, you need to look somewhere else. either deeper into the analysis pipeline or deeper into the physics. And either destination is fascinating because it means that one of the most carefully constructed models in the history of science is either subtly miscalibrated or fundamentally incomplete. You're floating somewhere between wakefulness and sleep now, and the universe is floating between two numbers that refuse to be the same. There's a strange comfort in that symmetry. Some of the biggest questions do not have answers yet. They just have better measurements. And sometimes the measurement is the discovery. You're going to leave the deep cosmos for a little while now and come closer to home. Not all the way home. Not to your bed, not to your street, not even to your solar system, although you will get there soon enough. Right now, you're going to visit a planet orbiting a dim red star about 120 light-years from Earth, a world called K2-18b, and what Webb found in its atmosphere might be the most consequential discovery in the history of biology, or it might be nothing. That uncertainty is what makes it so thrilling. K2-18b was first identified by the Kepler Space Telescope in 2015, and from the start it was an oddball. It orbits in the habitable zone of its host star, meaning it sits at a distance where liquid water could theoretically exist on the surface. But the planet itself is nothing like Earth. It is roughly 8.6 times the mass of our planet and about 2.6 times the radius. That puts it in a category astronomers call a sub-Neptune, bigger than Earth, smaller than Neptune, with no analogue in our own solar system. Sub-Neptunes are actually the most common type of planet in the galaxy, which is humbling because we do not have one, and apparently everyone else does. It is like discovering that every house on your street has a swimming pool, and you somehow missed the memo. Before Webb, observations by Hubble had already detected water vapour in K2-18b's atmosphere, which was exciting enough to generate headlines. But Hubble's data was limited. It could tell you that water was present but could not give you the full chemical inventory. Webb's near-infrared spectrograph, called NIRSpec, changed that completely. In September 2023, a team led by Nikku Madhusudhan at the University of Cambridge published results from Webb's transit spectroscopy of K2-18b, and the findings made the astronomical community sit up very straight. Transit spectroscopy is a beautifully simple technique in principle. You wait for the planet to pass in front of its star, and as it does, a thin ring of the planet's atmosphere is backlit by starlight. Different molecules in the atmosphere absorb light at different wavelengths, leaving distinctive fingerprints in the stellar spectrum. By comparing the star's spectrum with, and without the planet in the way, you can identify which molecules are present in the planet's air. It is like holding a glass of wine up to a lamp and deducing the grape variety from the colour of the shadow. Except the glass is 120 light-years away, and the lamp is a star. Webb's spectrum of K2-18b revealed clear detections of methane and carbon dioxide in the atmosphere. That alone was significant, because the combination of those gases, in the abundances observed, is consistent with a theoretical type of world called a Hycean planet, a planet with a hydrogen-rich atmosphere overlying a global ocean of liquid water. The Hycean hypothesis, proposed by Madhusudhan himself in 2021, suggests that sub-Neptunes in the habitable zone might host vast water oceans beneath thick but transparent hydrogen envelopes, creating conditions potentially friendly to life despite being radically different from Earth. The detection of methane and carbon dioxide, together with the apparent absence of ammonia, fit this picture surprisingly well. Ammonia should be present in a hydrogen-rich atmosphere unless something is removing it, and one mechanism that removes ammonia is dissolution in a liquid ocean. The chemistry was telling a coherent story, and the story involved water. But the headline grabber, the one that launched 1,000 breathless articles and at least as many cautious rebuttals, was the tentative detection of dimethyl sulfide, commonly abbreviated DMS. Dimethyl sulfide is a molecule that, on Earth, is produced overwhelmingly by living organisms, particularly marine phytoplankton. It is the compound largely responsible for the smell of the sea, that briny tang you notice at the coast. On Earth, there is no known significant abiotic source of DMS. If you detect it in an atmosphere, the simplest explanation is biology. Now, you need to pause here and breathe, both literally and scientifically. The detection of DMS on K218b was tentative. The signal was at the edge of statistical significance, meaning it could be real or it could be noise in the data. The Webb team was explicit about this, using careful language and flagging the need for additional observations. Follow-up programs have been allocated telescope time to look again with more sensitivity, and the results of those observations will either strengthen or eliminate the DMS signal. Until then, it remains a tantalizing possibility, not a confirmed detection. Science does not do victory laps on preliminary data, no matter how badly the public wants it to. Historians still argue whether the 1996 announcement of possible microbial fossils in the Martian meteorite, ALH 84001, helped or hindered the search for extraterrestrial life. That announcement, made with great fanfare at a NASA press conference attended by President Clinton, generated enormous excitement, followed by years of skepticism as alternative explanations for the observed features emerged. Many astrobiologists feel that the episode taught the community to be more cautious with biosignature claims, which is why the K218b team was so measured in their language. The lesson of ALH 84001 is that premature certainty about alien life can set the entire field back by decades. But here is the quirky thing that does not get enough attention. Even without DMS, the detection of methane and carbon dioxide in a habitable zone sub-Neptune is extraordinary. Before Webb, no telescope had ever measured these gases in the atmosphere of a small temperate exoplanet. The largest exoplanets, hot Jupiters roasting in tight orbits around their stars, had yielded atmospheric detections, but those worlds are hellscapes with no relevance to habitability. K2-18b is the first planet where the atmospheric chemistry is even plausibly consistent with a habitable surface environment. That is a milestone regardless of whether the DMS holds up. And K2-18b is not the only world Webb has tasted. The telescope has also measured the atmospheres of several planets in the TRAPPIST-1 system, a compact collection of 7 roughly Earth-sized worlds orbiting an ultra-cool red dwarf star about 40 light-years away. Early results have been mixed. Some of the innermost planets appear to have lost their atmospheres entirely, scorched away by the relentless ultraviolet flares of their host star. But the outer planets, particularly TRAPPIST-1e and F, which sit in or near the habitable zone, are still under investigation. Webb has also detected carbon dioxide in the atmosphere of WASP-39b, a hot Saturn orbiting close to its star, and has produced the most detailed atmospheric spectrum of any exoplanet ever obtained. The field of exoplanet atmospheric characterization has gone from theoretical speculation to observational reality in the span of 2 years, and almost all of that progress belongs to Webb. You're lying in the dark thinking about the smell of the ocean on a planet you will never visit, orbiting a star you cannot see with your naked eye, and somehow that feels like progress. It is. Slowly, molecule by molecule, spectrum by spectrum, Webb is building the toolkit that will eventually tell us whether life is unique to this pale blue dot or scattered across the galaxy like dandelion seeds in a summer breeze. The answer is not here yet, but for the first time in human history the question is testable, and that should make you feel something. Wonder maybe, or hope, or the particular kind of drowsy amazement that comes from realizing the universe might be more alive than you thought. The word biosignature sounds clinical, like something you would find on a medical form or an insurance document, but it's actually one of the most loaded terms in all of science, because it carries the implicit promise that life can be recognized from a distance, that you do not need to land on a world, scoop up a sample and put it under a microscope, that you can stand 120 light years away, squint through a golden mirror, and say with confidence, something is alive over there. The reality, as you might expect, is far messier than the promise. A biosignature in the context of exoplanet science is any observable feature of a planet that is best explained by the presence of life. It could be a gas in the atmosphere that should not be there without biology to produce it. It could be a pattern of reflected light from the surface that matches the spectral signature of photosynthetic pigments. It could be a chemical disequilibrium, a combination of gases that would normally react with each other and disappear, but persist because living organisms keep replenishing them. Earth's atmosphere is the textbook example of this disequilibrium. Oxygen and methane coexist in our air, which should not happen because they react together to form carbon dioxide and water. The only reason both persist is that photosynthetic organisms keep pumping out oxygen, while methanogenic archaea keep pumping out methane. If all life on Earth vanished tomorrow, the atmosphere would drift toward chemical equilibrium within a few million years, and a distant observer would see the biosignatures fade like a dying radio signal. The challenge is that almost every proposed biosignature has an abiotic alternative, a way to produce the same signal without life. Oxygen can be generated by the photodissociation of water vapour in a planet's upper atmosphere, where ultraviolet light splits water molecules and the lightweight hydrogen escapes to space, leaving oxygen behind. Methane can be produced by geological processes, volcanic outgassing, or hydrothermal reactions between water and rock. Even dimethyl sulfide, the star of the K218b story, could theoretically be produced by exotic photochemistry in a hydrogen-rich atmosphere, though no one has demonstrated a plausible abiotic pathway at the required abundances. The point is that no single molecule is a definitive indicator of life. What you need is context, a combination of gases in specific ratios on a planet with the right temperature and pressure that collectively cannot be explained by any known abiotic process. Life is not a single fingerprint. It is an alibi that has to be checked against every other possible suspect. This is why the scientific community has been so cautious about the K218b results, and why the broader search for biosignatures is framed as a long-term project rather than a single eureka moment. Webb is the first telescope capable of detecting potential biosignature gases in the atmospheres of small temperate exoplanets, but detecting a gas is only the first step. Interpreting what that detection means requires atmospheric modelling, photochemical simulations, geological plausibility assessments, and a healthy dose of epistemic humility. You have to ask not just whether biology could produce the signal, but whether anything else could produce it too, and then you have to evaluate the relative likelihood of each explanation given everything you know about the planet. It is detective work of the highest order, and the case files are still being assembled. One of the concepts that has gained traction in recent years is the idea of an ensemble biosignature, a set of atmospheric features that individually could be abiotic, but collectively point overwhelmingly toward biology. For instance, detecting oxygen, methane, and water vapour simultaneously in a terrestrial atmosphere would be very difficult to explain without life. Adding nitrous oxide, another gas produced primarily by biological processes on Earth, would strengthen the case further. The more gases you can detect, and the more tightly you can constrain their abundances, the harder it becomes for abiotic chemistry to mimic the pattern. Webb's spectroscopic capabilities are pushing toward this kind of multi-molecule detection, but even with its extraordinary sensitivity, the telescope is working at the edge of what is physically possible for planets as small and distant as those in the habitable zone. Here is a historical fact that adds perspective. The idea that you could detect life on other planets through atmospheric spectroscopy was first proposed seriously by James Lovelock in the 1960s, while he was working as a consultant for NASA on the Viking Mars mission. Lovelock argued that you did not need to go to Mars to look for life. You could simply analyse the Martian atmosphere from Earth. If it was in chemical equilibrium, it was probably dead. If it showed the kind of disequilibrium seen in Earth's atmosphere, something was keeping it out of balance. His analysis of Mars's atmosphere, which is dominated by carbon dioxide and close to equilibrium, led him to predict that the Viking landers would find no life. He was right, more or less, and the insight eventually led him to develop the Gaia hypothesis, the idea that Earth's biosphere actively regulates its own environment to maintain habitable conditions. Historians still argue whether the Gaia hypothesis is genuine science or a philosophical metaphor dressed in scientific clothing. But Lovelock's original insight about atmospheric biosignatures was unquestionably prescient. He saw the logic 60 years before Webb had the hardware to test it. The quirky footnote for this section involves a molecule you have almost certainly never heard of, phosphine. In 2020, a team led by Jane Greaves announced the detection of phosphine in the atmosphere of Venus, a finding that generated enormous excitement because phosphine on a rocky planet has no known abiotic source in sufficient quantities. The implication was that microbial life might exist in the acidic clouds of Venus, floating in a narrow temperate band high above the planet's hellish surface. The announcement was controversial from the start, with other researchers questioning the data analysis and proposing alternative explanations. The debate has continued for years without definitive resolution, and it serves as a cautionary tale for the K218b discussion. Atmospheric detections at the edge of instrument sensitivity are inherently fragile, and the history of astrobiology is littered with tantalizing signals that eventually evaporated under scrutiny. But here is why you should still feel cautiously electrified, even if the DMS signal on K218b turns out to be noise, even if every current biosignature candidate eventually finds an abiotic explanation. The fact that we are asking these questions with real data from real planets is unprecedented. A generation ago, exoplanets were theoretical. A decade ago, exoplanet atmospheres were mostly uncharacterized. Today, Webb is measuring the chemical composition of air on worlds orbiting other stars, and the next generation of telescopes, the extremely large telescope, the Habitable Worlds Observatory, will push the sensitivity even further. The question of whether we are alone in the universe has shifted from philosophy to chemistry. It is no longer a matter of belief, it is a matter of spectra, and spectra, unlike beliefs, can be checked. You are moving through this night the way light moves through an atmosphere, slowly, bending around obstacles, picking up information with every interaction. The search for life beyond Earth is not going to end tonight. It may not end in your lifetime, but the tools are sharper than they have ever been, and the universe, as Webb keeps reminding us, is full of surprises. Some of those surprises are closer than you think, much closer. Because Webb has not only been staring at distant stars, it has also turned its gaze back toward our own cosmic neighbourhood, and what it found among the planets and moons you grew up learning about in school is enough to make you reconsider everything you thought you knew about the solar system. You might think that a telescope designed to see the edge of the observable universe would have little interest in Jupiter. Jupiter is right there. It is the largest planet in your solar system, visible to the naked eye on a clear night, so familiar it practically has a seat at the family dinner table. But Webb's infrared vision reveals a Jupiter you have never seen before. a Jupiter that is alien and violent and beautiful in ways that visible light images cannot convey. And the scientists who study planetary atmospheres were just as eager to point Webb at the gas giant as the cosmologists were to aim it at the deep field. The images arrived in August 2022, and they were immediately iconic. In visible light, Jupiter looks like a butterscotch marble streaked with brown and white bands. In Webb's infrared view, the planet glowed like an ember. The famous Great Red Spot, a storm system larger than Earth that has been raging for at least 350 years, appeared as a bright white patch because its high-altitude clouds reflect a lot of sunlight and show up prominently in near-infrared. The bands of atmosphere, zones and belts driven by Jupiter's ferocious winds, which can exceed 400 kilometers per hour, were rendered in shades of blue, orange and green in the false color composite, each shade corresponding to a different altitude and chemical composition. You could see auroras blazing at both poles, rings of ultraviolet light created by charged particles from the sun spiraling along Jupiter's immense magnetic field lines and crashing into the upper atmosphere. Earth has auroras too, of course, the northern and southern lights, but Jupiter's are hundreds of times more energetic and permanently active. What Webb added beyond the visual spectacle was chemical detail. Its spectrographs dissected Jupiter's atmosphere layer by layer, measuring the abundances of ammonia, methane, water vapour and phosphine at different altitudes and latitudes. This vertical profiling is crucial for understanding Jupiter's weather, which operates on principles fundamentally different from Earth's. On our planet, weather is driven primarily by solar heating and the evaporation of water from the oceans. On Jupiter, much of the energy driving the atmosphere comes from the planet's own interior, leftover heat from its formation, still radiating outward after 4.6 billion years. Jupiter emits nearly twice as much energy as it receives from the Sun. It is in a sense a failed star, a ball of hydrogen helium that almost made it to the fusion threshold, but fell short by a factor of about 80 in mass. That is the most relatable thing about Jupiter. It tried its best and came up short, which is something most of us can sympathise with at 3 in the morning. Webb also captured something Hubble had never shown clearly: Jupiter's faint ring system. Yes, Jupiter has rings. Most people do not know this because Jupiter's rings are not the gorgeous, icy spectacles of Saturn. They are thin, dusty, and nearly invisible in optical light. They were first discovered by the Voyager 1 spacecraft in 1979, a finding so unexpected that the mission team initially thought the images were a processing error. Webb's infrared sensitivity made the rings glow against the blackness of space, and for the first time you could see them in an image alongside the full disk of the planet and 2 of its smaller moons, Amalthea and Adrastea, which looked like tiny bright specks hovering in the void. Saturn, meanwhile, got its own Webb portrait, and it was equally revelatory. Saturn's rings are among the most studied structures in the solar system, but Webb's mid-infrared instrument, MIRI, showed them in a completely new light, literally. At mid-infrared wavelengths, the planet itself appeared almost completely dark because methane in its upper atmosphere absorbs nearly all incoming sunlight at those wavelengths. The rings, however, blazed brightly because they are made of water ice particles that reflect and emit infrared radiation at different rates than the methane-rich atmosphere. The result was a ghostly image, a dark disk surrounded by glowing rings, like a photographic negative of every Saturn picture you've ever seen. It was eerie and gorgeous, and it immediately became one of those images that makes you realise how much of the universe is hidden in wavelengths your eyes cannot see. Here is a historical fact worth knowing. Galileo was the first to observe Saturn through a telescope in 1610, but his instrument was so crude that he could not resolve the rings. He thought the planet had 2 large moons, one on each side, and was baffled when they seemed to disappear 2 years later as Saturn's rings tilted edge onto Earth. He reportedly wrote that Saturn had swallowed its children, a reference to the Greek myth of Kronos devouring his offspring. It took another 45 years before Christian Huygens, using a better telescope, correctly identified the rings as a flat disk surrounding the planet. Historians still argue whether Galileo would have figured it out himself given more time and better optics, or whether his theoretical framework for planetary motion was too limited to accommodate the concept of a ring system. But the solar system observations that truly electrified the astrobiology community were not of Jupiter or Saturn themselves. They were of the moons. Jupiter's moon Europa and Saturn's moon Enceladus have been prime targets in the search for extraterrestrial life for decades, because both are believed to harbour liquid water oceans beneath their icy crusts. Europa's ocean is inferred from the moon's smooth, fractured surface, its induced magnetic field, and the way it flexes under Jupiter's tidal forces. Enceladus announced its ocean more dramatically, spraying geysers of water vapour and ice particles from fissures near its south pole, first observed by the Cassini spacecraft in 2005. Webb has observed both moons, and the Enceladus results in particular were remarkable enough to deserve their own section, which is exactly where you are headed next. But before you leave Jupiter and Saturn behind, there is a quirky detail about Webb's solar system work that is worth appreciating. The telescope was not originally designed to observe objects this close. Its guidance system was built to track distant stars, which move very slowly across the sky. Planets and moons in our solar system move much faster, and pointing Webb at them required special modifications to the telescope's tracking software. Engineers had to develop a mode called moving target tracking, which allows the telescope to follow objects as they drift across the field of view. The fact that they managed to make a telescope optimized for the most distant objects in the universe also work for the closest objects is a testament to the flexibility of the design and the stubbornness of the operations team. You're drifting through the solar system now, past the gas giants and their icy entourages, and the air is getting interesting. Not Earth's air, the air escaping from tiny frozen moons where no one expected to find anything warm at all. The next thing Webb saw shooting from one of those moons was so dramatic, so unexpectedly vast, that it forced scientists to reconsider just how much water might be hiding in the cold, outer reaches of your own neighbourhood. Enceladus is small, absurdly small by planetary standards. It is roughly 500 kilometers in diameter, which means you could fit it comfortably inside the state of Arizona, or for a more European sense of scale, it is slightly smaller than Spain's width from east to west. It is one of Saturn's 80-plus moons, and for most of the history of astronomy it was considered a frozen, geologically dead ice ball of no particular interest. Voyager 2 flew past it in 1981 and sent back images of a bright cratered surface that looked about as exciting as a snowbank. Nobody gave it a second thought. Then Cassini arrived at Saturn in 2004 and everything changed. The spacecraft's instruments detected something extraordinary near Enceladus's south pole, a region of anomalously high temperature, crisscrossed by 4 parallel fractures in the ice that scientists nicknamed the tiger stripes. And from those tiger stripes, plumes of water vapour and ice particles were erupting into space with enough velocity to escape the moon's feeble gravity and feed directly into Saturn's E-ring, the faint outermost ring of the planet. Enceladus was not dead. It was alive in the most dramatic possible way, venting its internal ocean into the vacuum of space like a fire hydrant with no cap. Cassini spent the next 13 years studying those plumes, even flying directly through them to sample their contents. What it found was remarkable. The plumes contained not just water, but sodium chloride, table salt, suggesting the water had been in prolonged contact with a rocky seafloor. They contained silica nanoparticles, which on Earth form only in hydrothermal systems where hot water interacts with rock at temperatures above about 90 degrees Celsius. And in 2018, analysis of Cassini data revealed the presence of complex organic molecules, large carbon-bearing compounds with molecular weights above 200 atomic mass units. Not life, not even close to proof of life. But the ingredients were there: liquid water, heat, minerals, organic chemistry. Enceladus had quietly become one of the most promising places in the solar system to look for extraterrestrial biology. And then Webb looked at it, and the scale of what was happening turned out to be far larger than anyone had imagined. In November 2022, Webb's NIR SPEC instrument observed Enceladus and detected a water vapor plume extending an astonishing distance from the Moon. Previous observations by Cassini had measured plumes reaching a few hundred kilometers above the surface. Webb's data showed water vapor extending over 9,600 kilometers, roughly 20 times the diameter of the Moon itself. That is like standing next to a golf ball and watching it spray a jet of water across an entire football field. The plume was not just large, it was so expansive that Webb could see it feeding water vapor into a diffuse torus of material encircling Saturn along Enceladus's orbital path. The tiny moon was not just leaking, it was actively resupplying its corner of the Saturnian system with fresh water, molecule by molecule, eruption by eruption. The rate was staggering. Webb's measurements estimated that Enceladus was ejecting roughly 300 kilograms of water per second. 300 kilograms every second. To put that in relatable terms, that is enough water to fill an Olympic swimming pool in a couple of hours, and it has been doing this for who knows how long, potentially millions of years. Historians still argue whether Giovanni Cassini, the 17th century astronomer for whom the spacecraft was named, would have been more astonished by the discovery of the plumes, or by the fact that a telescope named after a NASA administrator was floating 1 million miles from Earth, observing them. The 17th century was a time when the moons of Saturn were barely resolved as points of light. The idea that one of those points was spraying water into space would have been incomprehensible. The energy source driving this activity is tidal heating. Enceladus orbits Saturn in an orbital resonance with the larger moon Dione, which keeps Enceladus's orbit slightly elliptical. As the moon moves closer to and farther from Saturn on each orbit, the planet's immense gravity flexes the moon's interior, generating friction and heat. It is the same mechanism that heats Jupiter's moon Io into the most volcanically active body in the solar system, but on Enceladus the result is gentler, warm water instead of molten lava. The tidal heating maintains a liquid ocean beneath roughly 20 to 25 kilometers of ice, and the pressure of that ocean, combined with the fractures at the South Pole, drives the plumes. Here's the quirky detail that makes Enceladus particularly tantalizing for astrobiologists. On Earth, some of the most ancient and resilient life forms are found at hydrothermal vents on the ocean floor, places where superheated water laden with minerals erupts from cracks in the Earth's crust. These ecosystems do not depend on sunlight. They run on chemical energy, drawing power from reactions between the hot vent fluid and the surrounding seawater. If similar vents exist on Enceladus's seafloor, and the Cassini silica data strongly suggest they do, then the moon has all the basic requirements for life as we understand it. Liquid water, chemical energy, organic molecules, mineral surfaces that could catalyze reactions. You do not need sunlight. You do not need a breathable atmosphere. You just need chemistry and time, and Enceladus has plenty of both. Webb's detection of the enormous plume added a new dimension to the conversation. If water is escaping at such prodigious rates, it means the subsurface ocean is vigorously connected to the surface, at least at the South Pole. That connection is a two-way street. Material from the ocean gets ejected into space, but material from the surface and the ice shell could also be cycling back into the ocean, creating a dynamic chemical environment that could support the kind of disequilibrium life needs to thrive. Some researchers have even speculated that a future mission could fly through the plume, as Cassini did, but with instruments specifically designed to detect biosignatures, amino acids, lipids, metabolic byproducts. You would not need to land on the moon or drill through 20 kilometers of ice. The ocean is delivering itself to you, gift wrapped in a column of vapor and ice crystals. NASA's proposed Enceladus Orbilander mission concept, which would orbit the moon and eventually land near the Tiger Stripes, has been discussed in multiple decadal survey reports, though it has not yet been formally funded. The European Space Agency has also expressed interest in Enceladus missions. Webb's discovery of the plume's true scale has added urgency to these proposals, because it demonstrated that the moon's activity is not a trickle but a torrent, and that the window for studying it might be wider than previously assumed. You are lying somewhere warm and dry, which is more than can be said for the interior of Enceladus, where a dark ocean sloshes against a rocky floor in a silence deeper than anything you have ever experienced. No wind, no waves, just water, rock, heat, and the faintest possibility that something down there is alive and has been alive for a very, very long time, completely unaware that a golden mirror a billion kilometers away just noticed its bathwater escaping into space. You're going to shift your gaze now from tiny moons with hidden oceans to something far grander and far more visually overwhelming. You're going to step inside a stellar nursery, a place where stars are being born right now, as you listen to this, in clouds of gas and dust so enormous that your brain will refuse to process the scale no matter how many analogies you're offered. This is where Webb has produced some of its most breathtaking images, the ones that make people who have never cared about astronomy suddenly stop scrolling and stare. And beneath the beauty, there is science so rich it will take decades to fully digest. The image that broke the most hearts was the cosmic cliffs, Webb's near-infrared portrait of a region in the Carina Nebula, released as part of that first batch of images in July 2022. The Carina Nebula is one of the largest and most active star-forming regions in the Milky Way, located about 7,600 light-years from Earth in the southern sky. Hubble had photographed it before, and those images were stunning. Towering pillars of gas sculpted by the radiation of young, massive stars glowing in shades of amber and turquoise. But Hubble saw the surface. Webb saw through. In the infrared, the thick curtains of dust that obscure the interior of the nebula become translucent. Webb's image revealed a landscape that looked like a rugged mountain range at sunset, a cliff face of gas and dust stretching across light years, its edge carved by the ultraviolet radiation and stellar winds pouring off the hot young stars above it. And behind that cliff, hidden from Hubble's view, were hundreds of previously unseen baby stars in various stages of formation. Some were still embedded in dense knots of gas, glowing only in infrared as they slowly accumulated mass from their surroundings. Others had already ignited hydrogen fusion in their cores and were beginning to blow cavities in the cloud, clearing space around themselves like children kicking off blankets. The image was not just beautiful, it was a census of stellar birth, captured at a resolution that revealed individual protostars for the first time in a region that Hubble had only been able to sketch in broad strokes. The process of star formation is one of those things that sounds simple in a textbook and turns out to be ferociously complicated in practice. The basic story goes like this. a cloud of molecular gas, mostly hydrogen, floats in interstellar space. Something perturbs it. A shock wave from a nearby supernova, the passage of a spiral density wave through the galaxy, or just the random gravitational jostling of neighbouring clouds. The perturbation creates regions of slightly higher density, and those regions begin to collapse under their own gravity. As the gas falls inward, it heats up. A dense, rotating core forms at the centre, surrounded by a flattened disk of gas and dust. When the temperature and pressure at the core reach about 10 million degrees, hydrogen nuclei begin fusing into helium, and a star is born. But the details are where the devil lives. How does the collapsing gas shed its angular momentum, which would otherwise spin it apart before it could form a star? How does magnetic pressure, which threads through molecular clouds like invisible elastic bands, get overcome? What determines the final mass of the star? Why do some clouds produce monsters 100 times the mass of the Sun, while others produce dim red dwarfs 1/10 of its mass? These are open questions, and Webb is providing data that bears directly on all of them. One of the most important contributions has been Webb's ability to observe protoplanetary disks, the flattened disks of gas and dust around young stars from which planets will eventually form. These disks had been studied extensively by ground-based telescopes and by the Atacama Large Millimeter Array, ALMA, a radio telescope in Chile that can map dust emission at high resolution. But Webb adds the infrared dimension, revealing the chemical composition of the disk material in ways that radio observations alone cannot. Webb has detected water ice, carbon dioxide ice, and a variety of organic molecules in protoplanetary disks around young stars in the Orion Nebula and other nearby star-forming regions. These detections matter because they tell you what ingredients are available for planet formation. The chemistry of the disk determines the chemistry of the planets, which determines whether those planets can support liquid water, organic chemistry, and potentially life. Every detection is a data point in the story of how habitable worlds are built. Historians still argue whether the nebula hypothesis of solar system formation, first proposed by Immanuel Kant in 1755 and independently by Pierre-Simon Laplace in 1796, should be considered a genuine scientific theory or a philosophical speculation that happened to be correct. Kant and Laplace had no observational evidence for protoplanetary disks. They simply reasoned that a rotating cloud of gas would naturally flatten into a disk and condense into a central star surrounded by orbiting bodies. The fact that this reasoning turned out to be essentially right, confirmed by centuries of subsequent observation, and now visualized in exquisite detail by Webb, is either a testament to the power of deductive logic or a spectacular lucky guess. Perhaps both. Here is the quirky detail from the nurseries. Among the young stellar objects Webb has observed in the Carina Nebula and elsewhere are so-called Herbig-Haro objects, narrow jets of gas ejected at high speed from the poles of forming stars. These jets can extend for light years, ploughing into the surrounding medium and creating glowing shock fronts where the jet material collides with the ambient gas. Webb's infrared images of Herbig-Haro objects have revealed intricate knotted structures within the jets that are invisible in optical light, suggesting that the ejection process is episodic rather than continuous. The star hiccups, essentially, launching blobs of material at irregular intervals. Some researchers have compared the pattern to a cosmic Morse code, though what message is being sent and to whom remains a matter of poetic rather than scientific interpretation. The pillars of creation also received the Webb treatment, and the result was predictably magnificent. Hubble's 1995 image of the pillars, those three towering columns of gas in the Eagle Nebula, is arguably the most famous astronomical photograph ever taken. Webb's version, released in October 2022, showed the same structures in near-infrared, and the effect was transformative. The opaque pillars became semi-transparent, revealing the stars forming inside them like candles glowing through frosted glass. The edges of the pillars, where ultraviolet radiation from nearby massive stars is eroding the gas, appeared sharp and crimson in Webb's false colour rendering, and scattered across the image, in the spaces between the pillars, were dozens of young stars with diffraction spikes, those distinctive six-pointed starburst patterns caused by Webb's hexagonal mirror segments, each one a reminder that you're looking at a real place, a real factory, where new solar systems are being assembled right now out of the same raw materials that built yours 4.6 billion years ago. You're deep in the nursery now, surrounded by dust and light and the slow, gravitational patience of clouds that have been collapsing for hundreds of thousands of years. It is warm in here, at least conceptually. New things are being made, and soon some of those new things will grow old and die. And when they do, Webb will be watching that too. Stars die. That is not a metaphor or a philosophical observation. It is a physical inevitability built into the nuclear reactions that make them shine. Every star is a temporary truce between gravity, which wants to crush it, and radiation pressure, which wants to blow it apart. As long as the star has fuel to burn, hydrogen fusing into helium, helium into carbon, carbon into heavier elements up the periodic table, the truce holds, but fuel runs out. And when it does, gravity wins, and the star's death can be one of the most spectacular events in the observable universe. Webb has been watching these deaths unfold, and the portraits it has taken of dying stars have revealed structures and processes that even seasoned astronomers did not expect. The poster child for Webb's end-of-life observations is the Southern Ring Nebula, also known as NGC 3132, which was one of the 5 targets featured in the first image release in July 2022. A planetary nebula, which, despite the name, has absolutely nothing to do with planets, is a shell of gas expelled by a dying star in the final stages of its life. When a star like the Sun exhausts its hydrogen fuel, it swells into a red giant, puffing off its outer layers in a series of thermal pulses that send concentric shells of gas billowing outward into space. The hot, dense core left behind, called a white dwarf, bathes these shells in ultraviolet radiation, causing them to fluoresce in gorgeous patterns of colour and light. The whole structure is temporary. Within a few tens of thousands of years, the shells dissipate into the interstellar medium, enriching it with the heavy elements the star forged during its lifetime. Planetary nebulae are not just beautiful, they are recycling centres, returning processed material to the galaxy so that new stars and planets can be built from it. Hubble photographed the Southern Ring Nebula years ago, and the image showed a classic structure, concentric rings of glowing gas surrounding a bright central star. But there was always something slightly odd about it. The central star seemed too bright and too cool to be the white dwarf responsible for ionizing the nebula. The suspicion was that there was a second star hidden nearby, a companion that was blending its light with the true source. Hubble could not separate them. Webb could. In the near-infrared image, both stars were clearly resolved for the first time. The brighter star, the one Hubble had been staring at for years, turned out to be a younger, less evolved companion that played no role in creating the nebula. The actual culprit, the dying white dwarf, was the fainter of the two, sitting right beside its companion like a quiet arsonist standing next to a bystander while the building burns. Webb's mid-infrared image, taken with the MIRI instrument, was even more revealing. It showed the white dwarf surrounded by intricate spiral patterns in the dust, patterns that astronomers interpreted as evidence that the two stars had been orbiting each other for a long time, with their gravitational interactions sculpting the outflowing material into a complex, three-dimensional structure. The nebula was not a simple expanding bubble. It was a gravitationally choreographed dance of gas and dust, shaped by the orbital dynamics of a binary system over thousands of years. And there was more. Careful analysis of the Webb images suggested the possible presence of a third star even farther out, based on additional arc-like structures in the nebula that did not fit a two-body model. The southern ring, it seemed, was not a solo performance or even a duet. It might be a trio, and the complexity of the system was written in the shapes of its dying breath. Historians still argue whether the term planetary nebula, coined by William Herschel in the 1780s because these objects looked vaguely planet-like through his small telescope, has caused more confusion than any other misnomer in astronomy. It probably has. Generations of students have walked into introductory astronomy courses expecting planetary nebulae to involve planets, only to be told that the name is a historical accident. It is the astronomical equivalent of calling a koala a bear, technically wrong, universally accepted and too late to change. Here is the quirky detail that makes dying stars even more fascinating than you might expect. The elements expelled by planetary nebulae include carbon, nitrogen, and oxygen, the building blocks of organic chemistry. But the details of which elements are produced and in what quantities depend on the star's initial mass, its metallicity, and the poorly understood physics of convective mixing in its interior during the red giant phase. Different models predict different yields, and the discrepancies have real consequences for our understanding of galactic chemical evolution. Webb's ability to measure the chemical composition of planetary nebulae with unprecedented precision is helping to resolve some of these discrepancies, molecule by molecule. Beyond planetary nebulae, Webb has also observed the remnants of more violent stellar deaths, supernovae. When a star more than about 8 times the mass of the Sun exhausts its fuel, the collapse is not gentle. The core implodes in milliseconds, bounces, and sends a shockwave tearing through the outer layers of the star at tens of thousands of kilometers per second. The explosion briefly outshines the entire host galaxy, scattering heavy elements, iron, nickel, cobalt, gold, uranium, across light years of space. What remains is either a neutron star, an object so dense that a teaspoon of it would weigh 1 billion tons, or, if the progenitor was massive enough, a black hole. Webb observed the supernova remnant Cassiopeia A, the expanding debris cloud from a star that exploded roughly 340 years ago, and the infrared images revealed previously unseen details in the ejecta. Knots of silicon and iron glowed in the mid-infrared, tracing the chaotic, asymmetric explosion that tore the star apart. A structure near the centre of the remnant, dubbed the Green Monster by the science team for its colour in the false colour composite, turned out to be a sheet of shock-heated gas ploughing into the surrounding interstellar medium, lighting up like a neon sign as it collided with material expelled by the star before it exploded. The calcium in your bones, the iron in your blood, the oxygen in the air you are breathing right now. All of it was manufactured inside stars that lived and died billions of years before the Sun was born. Every atom heavier than lithium in your body is stellar ash, recycled through supernova explosions and planetary nebulae, and mixed back into the interstellar medium to be incorporated into new stars, new planets, and eventually new people lying in dark rooms listening to stories about telescopes. Webb is not just photographing the deaths of stars, it is photographing the origin of the material world, the forges where the periodic table was built, one cataclysm at a time, and those cataclysms, violent as they are, eventually lead to something constructive. New structure, new complexity, new chemistry. Even destruction, in the right context, is creative. Not all destruction is a solo act. Sometimes galaxies die together, tangled in each other's gravity, ripping stars from their orbits and flinging gas across millions of light years, in collisions so slow and so enormous that no human lifetime could witness more than a single frozen frame. Galaxy mergers are among the most violent events in the universe, and Webb has captured them with a clarity that makes previous images look like sketches on a foggy window. The showcase piece is Stephan's Quintet, a visual grouping of 5 galaxies in the constellation Pegasus that was one of the original 5 targets in Webb's first image release. The image was the largest Webb had produced at that point, composed of roughly 1,000 individual exposures stitched together into a mosaic covering an area of sky about 1/5 the diameter of the Moon. And the detail was staggering. You could see individual star clusters in galaxies 290 million light-years away. You could trace tidal tails, long, luminous streamers of stars and gas pulled out of their parent galaxies by gravitational interaction, stretching across the frame like brush strokes. You could see shockwaves propagating through intergalactic gas, where one galaxy, NGC 7318b, is plunging through the group at roughly 3.2 million kilometers per hour, driving a bow shock that heats the surrounding medium to tens of millions of degrees. The quirky detail about Stephan's Quintet is that it is not actually a quintet in the physical sense. One of the 5 galaxies, NGC 7320, is a foreground interloper sitting about 40 million light-years from Earth, roughly 7 times closer than the other 4. It just happens to lie along the same line of sight, like a photobomber standing in front of a group portrait at a wedding. The remaining 4 galaxies are genuinely interacting, caught in a slow gravitational embrace that has been distorting their shapes for hundreds of millions of years. Webb's infrared view revealed this layered structure with new clarity, separating the foreground galaxy's resolved stars from the more distant galaxy's diffuse glow in a way that visible light images could not easily achieve. But the scientific meat of the Stephan's Quintet observation was in the shockwave. When NGC 7318b plows through the intergalactic gas, it creates a region of compressed, superheated material that emits strongly in the mid-infrared. Webb's MIRI instrument mapped this shock front in detail, revealing molecular hydrogen emission, the signature of warm gas being violently stirred and heated by the collision. This matters because molecular hydrogen is the raw material for star formation, and understanding how shocks process and redistribute it is essential for understanding how galaxy mergers trigger or suppress the formation of new stars. Some mergers ignite furious bursts of star formation as gas is compressed by the interaction. Others seem to quench it, heating the gas so thoroughly that it cannot cool and collapse. The physics that determines which outcome prevails is still poorly understood, and Webb's observations of Stephan's Quintet are providing some of the most detailed constraints yet. Galaxy mergers are not rare events. They're a fundamental part of how the universe builds structure. The hierarchical assembly model you heard about earlier, small things merging into bigger things over cosmic time, applies not just to dark matter halos and protogalaxies, but to the full-grown galaxies you see today. The Milky Way itself has consumed numerous smaller galaxies over its history, and the evidence is written in its structure. Streams of stars with unusual orbits, remnants of tidally disrupted dwarf galaxies, can be found threading through the Milky Way's halo like loose threads in a tapestry, and the Milky Way is not done merging. In roughly 4 to 5 billion years, it will collide with the Andromeda Galaxy, our nearest large galactic neighbour, in a merger that will eventually produce a single, larger elliptical galaxy, and formally dubbed Milkdromeda, which is the most delightfully ridiculous name in all of astrophysics. Historians still argue whether the first person to identify galaxy interactions as a significant process in cosmic evolution was Fritz Zwicky, who studied peculiar galaxies in the 1930s and 1940s, or Halton Arp, who compiled a famous catalogue of peculiar galaxies in 1966. ARP's Atlas of Peculiar Galaxies documented hundreds of systems with unusual morphologies, bridges, tails, rings, shells, and many of these turned out to be galaxies caught in the act of merging. At the time, the significance of mergers was underappreciated. Most astronomers viewed galaxies as relatively static, isolated island universes that evolved primarily through internal processes. The idea that collisions and mergers were common and important took decades to gain acceptance, driven in large part by computer simulations that showed how gravitational interactions could reproduce the bizarre shapes ARP had catalogued. Webb is now observing merging systems not just in the local universe, but at high redshifts, catching galaxy collisions in the act billions of years ago, when the universe was younger and denser and mergers were even more frequent. Some of the impossible galaxies from the early universe, those massive objects at redshift 8 or 10 that should not have assembled so quickly, may have gotten their head start through early mergers, rapid collisions of smaller proto-galaxies that pooled their gas and stars into a single large system much faster than the smooth, gradual accretion models predicted. Webb's high-resolution imaging can sometimes distinguish between a single massive galaxy and a tight group of smaller galaxies in the process of merging, and this distinction has real consequences for interpreting the early galaxy crisis. If some of those impossible galaxies are actually multiple objects caught mid-collision, their individual masses might be less alarming. The crisis softens, though it does not disappear entirely. There is a strange beauty in galaxy mergers that is easy to miss if you focus only on the violence. Yes, stars are flung into intergalactic space. Yes, gas is heated to millions of degrees. Yes, supermassive black holes at the centres of merging galaxies will eventually spiral toward each other and coalesce in a burst of gravitational waves that shakes the fabric of space-time itself. But mergers also create. They trigger star formation. They build larger, more complex structures. They redistribute heavy elements across vast volumes. The tidal tails pulled out during an interaction can condense into new dwarf galaxies, tiny systems born from the debris of a collision like wildflowers sprouting in the scar of a forest fire. Even the supermassive black hole merger, for all its violence, releases energy that can regulate the growth of the resulting galaxy, preventing it from forming stars too quickly and burning through its gas supply. Destruction and creation are not opposites in the cosmos. They are collaborators, and Webb is documenting their partnership with the dispassionate clarity of an instrument that has no preference for either. You're floating through a universe that builds itself by tearing itself apart, and somehow the result is structure, complexity, and light. The collisions continue, the mergers proceed, and Webb keeps watching, patient and cold, recording every tidal tail and shockwave with the detached precision of something that will never need to sleep. You've travelled from the nearby moons of Saturn to the violent mergers of distant galaxies, and now you're going to push further than any human-made instrument has ever reached. You're going to the edge. Not the edge of space, because space may not have an edge, but the edge of time, the earliest moment from which light has had a chance to reach us since the universe became transparent. And what Webb found there, at the very boundary of the observable universe, is a faint reddish smudge that does not look like much, but represents something almost incomprehensible. It is the most distant object ever seen by human eyes, or rather, by a human-built instrument that translates infrared photons into data that human brains can process into something resembling understanding. The object is called JADES-GS-Z14-0, and you heard its name briefly during the discussion of impossible galaxies, but it deserves its own moment because the story of its discovery and confirmation is a masterclass in how modern astronomy operates at the frontier. The galaxy was identified in data from the JD's survey, the JJSWST Advanced Deep Extragalactic Survey, a program that devoted hundreds of hours of Webb's time to imaging and spectroscopy of two small patches of sky, previously observed by Hubble as part of the Great Observatory's Origins Deep Survey. The goal was to find the most distant galaxies in the universe, and JD's delivered. The candidate was first spotted as a faint red dropout in Webb's NIRCam images. A dropout is an object that is visible in longer wavelength filters, but completely disappears in shorter wavelength ones. This disappearance happens because neutral hydrogen gas in the intergalactic medium absorbs light at wavelengths shorter than a specific threshold called the Lyman break. The more distant the galaxy, the more its Lyman break gets redshifted toward longer wavelengths, and the more filters it drops out of. By counting which filters the object disappears in, you get a rough estimate of its redshift. For JD's GSZ 14-0, the photometric estimate placed it at a redshift somewhere above 14. If correct, that would make it the most distant galaxy ever detected, its light emitted when the universe was only about 290 million years old. But photometric estimates, as you know by now, can be fooled. Dusty galaxies at lower redshifts can mimic the colours of high redshift objects, and the history of record-breaking distance claims is littered with candidates that did not survive spectroscopic scrutiny. So the JD's team requested follow-up spectroscopy with Webb's NIR spec instrument, which splits an object's light into a detailed spectrum and allows a precise measurement of the redshift from the position of spectral features. The observation was difficult. The galaxy is extraordinarily faint, and extracting a usable spectrum required hours of integration time, the infrared equivalent of leaving a camera shutter open in near total darkness and hoping that enough photons trickle in to form a pattern. The pattern formed. The spectroscopic redshift came back at 14.32, confirming that JD's GSZ 14-0 was indeed the most distant galaxy ever observed, its light originating from an epoch just 290 million years after the Big Bang. The universe at that point was roughly 2% of its current age. If the entire history of the cosmos were compressed into a single calendar year, this galaxy existed on January 7th. Everything humans have ever done, every civilization, every war, every love affair, every telescope, occupies the last fraction of a second before midnight on December 31st. And this little smudge of light was already there, shining in the first week of January. What makes the detection even more remarkable is the galaxy's properties. It is not a tiny, feeble ember. It extends across more than 1,600 light-years, which is small by modern galaxy standards but impressively large for something that young. Its ultraviolet luminosity suggests active star formation, and its spectrum shows evidence of oxygen emission, which, as you remember from earlier, requires at least one prior generation of stars to have formed, burned through their lives, and exploded, scattering their nucleosynthetic products into the surrounding gas. At 290 million years after the Big Bang, this galaxy had already lived through at least one complete stellar life cycle. The speed of cosmic evolution in the early universe continues to astonish. Historians still argue whether the quest to find the most distant object in the universe is driven more by genuine scientific curiosity or by the very human desire to hold a record. There is an undeniable competitive element to high redshift astronomy. Each new record breaker generates headlines, press releases, and citation counts. But the competition serves a purpose. because each new distance record pushes the instruments to their limits and forces researchers to develop better techniques for extracting signal from noise. The pursuit of the farthest galaxy is also the pursuit of the earliest galaxy, and the earliest galaxy tells you about the conditions of the universe at the dawn of star formation. There is real science at the finish line, even if the race to get there sometimes resembles a sprint more than a contemplative stroll. Here is the quirky detail about extreme redshifts that rarely makes it into popular accounts. At a redshift of 14.32, the light from JD's GSZ 14-0 has been stretched by a factor of 15.32, meaning its wavelength is now more than 15 times longer than when it was emitted. Light that started as ultraviolet, invisible to the human eye on the short wavelength side, has been pulled all the way through the visible spectrum and deep into the infrared. If your eyes could see infrared, the galaxy would appear as a deep, warm red, the colour of cooling embers, but your eyes cannot see infrared, which is why you needed a $10 billion golden mirror parked at the second Lagrange point to do it for you. The universe's most distant objects are hidden not because they are dark, but because their light has been stretched beyond the narrow band of wavelengths your biology happens to detect. They have been shining all along. You just did not have the right ears to hear them. The current redshift record will eventually be broken. Webb is still collecting data, and deeper surveys are planned that may push the frontier even further. There are theoretical predictions that galaxies could exist at redshifts of 17, 18, perhaps even 20, though at some point the universe becomes too young and too hot for stars to have formed at all. Finding the boundary, the true first moment of starlight, is one of Webb's ultimate goals. It is a boundary that recedes with every new discovery, like a horizon that moves as you walk toward it, and that is fitting, because the observable universe is itself a horizon, a sphere defined not by a physical wall but by the finite speed of light and the finite age of the cosmos. You are lying at the centre of your own observable universe right now, which is a fact that sounds egocentric but is actually just geometry. Every observer everywhere is at the centre of their own observable sphere, and somewhere near the edge of yours, a smudge of reddish light has been travelling for over 13 billion years to land on a mirror that humanity spent 30 years arguing about, building and finally launching on a Christmas morning. The photons do not care about the drama. They just arrive one by one, carrying a message from the beginning of everything. You've probably seen the headlines. They tend to arrive in breathless capital letters, shared by accounts with names like Cosmic Truth and Quantum Awakening, accompanied by thumbnails of web images overlaid with red arrows pointing at nothing in particular. James Webb Telescope disproves the Big Bang. Scientists in panic. Everything we knew was wrong. The Big Bang never happened. Here's the proof. The headlines are dramatic. They are shareable. They are, to put it gently, not accurate. But they are not entirely baseless either, and understanding the gap between what the headlines claim and what the science actually says is one of the most important things you can do as a person who cares about the universe and also about not being misled. The claim that Webb has disproved the Big Bang traces back to a confluence of real observations and aggressive misinterpretation. The real observations are the ones you've been hearing about all night, the impossible early galaxies, the supermassive black holes that grew too fast, the structures that appeared too mature for their age. These findings genuinely challenge aspects of the standard cosmological model, and the scientists who study them have said so openly in peer-reviewed papers and at conferences. The key word, though, is aspects. The challenges are to specific predictions within the Lambda CDM framework, predictions about how quickly galaxies assemble, how rapidly black holes grow, and how early structure formation can begin. They're not challenges to the Big Bang itself, which is a much broader and more robustly supported theory. This distinction matters, so let it settle in. The Big Bang theory, at its core, makes a handful of predictions that have been tested and confirmed with extraordinary precision. First, the universe is expanding. This was observationally established by Edwin Hubble in 1929 and has been confirmed by every subsequent measurement, including Webb's. Second, the universe was once much hotter and denser than it is today. The evidence for this is the cosmic microwave background, that faint afterglow of radiation filling the entire sky, measured by multiple satellite missions with results that match the Big Bang prediction to better than 1 part in 100,000. Third, the lightest elements, hydrogen, helium, and a trace of lithium, were produced in specific ratios during the first few minutes after the Big Bang, a process called Big Bang nucleosynthesis. The predicted ratios match the observed abundances in the oldest, most pristine gas clouds with remarkable accuracy. These 3 pillars, expansion, the CMB, and light element abundances, are the foundation of Big Bang cosmology, and none of them are threatened by anything Webb has found. What is threatened, or at least stressed, is the specific implementation of the Big Bang model encoded in lambda CDM. Lambda CDM is not the Big Bang. It is a particular parameterization of the Big Bang that includes specific assumptions about dark matter, dark energy, the initial spectrum of density fluctuations, and the subsequent growth of structure. It is the best model we have, and it fits an enormous range of data with impressive precision. But it is also a model, which means it is a simplification of reality, and simplifications can break when you push them into regimes they were not originally calibrated to describe. The early universe, the first few 100 million years, is exactly such a regime. Before Webb, there was almost no observational data from that epoch. Lambda CDM's predictions for that era were extrapolations, educated guesses based on physics that worked well at later times. Webb is now providing the first direct test of those extrapolations, and some of them are not passing. The media problem arises when the distinction between lambda CDM might need revision and the Big Bang is wrong collapses. These are fundamentally different statements. The first is normal science. Models get updated as new data arrives, and that is how progress works. The second is a revolutionary claim that would require discarding the 3 observational pillars mentioned above, which no Webb observation has done or even come close to doing. Conflating the two is like saying that discovering a new species of bird disproves the theory of evolution. It does not. It refines our understanding of how evolution operates in specific environments. Similarly, finding unexpectedly mature galaxies at high redshift does not disprove the Big Bang. It refines our understanding of how structure grows within the Big Bang framework. Historians still argue whether the media's tendency to frame scientific updates as paradigm-shattering revolutions is a modern phenomenon driven by social media incentives, or whether it has always been this way. There is evidence for the latter. When Alexander Friedmann first proposed an expanding universe in 1922, based on Einstein's equations of general relativity, the response was largely dismissive. Einstein himself initially called Friedmann's work suspicious and possibly erroneous before retracting his objection. When Georges Lemaitre independently derived a similar conclusion and suggested that the universe began from a primeval atom, the idea was mocked by Fred Hoyle, who coined the term Big Bang as a derisive label during a BBC radio broadcast in 1949. The name stuck, the derision did not, but the pattern of initial resistance followed by eventual acceptance is a recurring theme in cosmology. New ideas are always unsettling, and the public narrative always lags behind the scientific conversation. Here is the quirky and somewhat ironic footnote. Eric Lerner, the most prominent critic to claim that Webb's data disproves the Big Bang, published an article in 2022 that went viral, accumulating millions of views and becoming one of the most widely shared pieces of popular science writing that year. Lerner has been advocating against Big Bang cosmology since the 1990s, promoting an alternative model based on plasma physics that the overwhelming majority of cosmologists consider inconsistent with the observational evidence. His article cherry-picked real Webb results, the early massive galaxies, the unexpectedly bright objects, and presented them as fatal blows to the Big Bang while omitting the vast body of evidence that supports it. The article was persuasive to non-experts, precisely because it contained real data points embedded in a misleading narrative framework. It is a textbook example of how genuine scientific uncertainty can be weaponized to support a predetermined conclusion, and it serves as a reminder that the ability to read a scientific result is not the same as the ability to interpret one. The honest situation, as of the latest data, is this. The Big Bang is fine. Lambda CDM is stressed. The early universe formed stars, galaxies, and black holes faster than the standard model predicted. This could mean that star formation was more efficient in primordial conditions, that dark matter behaves differently on small scales, that the initial density fluctuations had more power on certain scales than currently assumed, or that some entirely new physical process was at work in the first few 100 million years. All of these are active areas of research. None of them require abandoning the Big Bang. What they do require is humility, which is the least glamorous but most essential ingredient in good science. The universe is not obligated to match your model. When it does not, you update the model. You do not throw a tantrum, and you do not throw a press conference claiming everything's broken. You go back to the data, you refine your assumptions, and you try again. Webb is providing the data, the refinement is underway, and the universe, as always, is patiently waiting for you to catch up. So where does the golden mirror go from here? You might think that after rewriting the timeline of galaxy formation, challenging dark matter models, sharpening the Hubble tension, tasting alien atmospheres, and capturing the most distant light ever recorded, Webb might be running low on ambitions. It is not. The telescope is still in its early years, and the observation programs lined up for its future cycles read like a wish list compiled by every subfield in astronomy simultaneously, each one convinced that their targets are the most important. They are probably all right. Webb's nominal mission lifetime was set at 5 years, which would have taken it to roughly mid-2027. But the telescope has a secret advantage that almost nobody talks about outside of engineering circles. During launch, the Ariane 5 rocket performed so precisely that Webb used significantly less of its onboard fuel for course corrections than planned. That fuel, hydrazine and dinitrogen tetroxide stored in tanks at the base of the sunshield, is the ultimate limiting factor for the mission, because Webb needs small thruster firings every few weeks to maintain its orbit around the L2 point. Less fuel used during insertion means more fuel available for station keeping, which means a longer mission. Current estimates suggest Webb has enough fuel for at least 20 years of operation, potentially longer. 20 years! That is not a mission. That is a career. Some of the graduate students analysing Webb's first data will be tenured professors before the fuel runs out. The observation programs planned for the near future span an almost absurd range of scales. On the smallest end, Webb will continue monitoring objects within our own solar system, tracking seasonal changes on Uranus and Neptune, whose atmospheres are poorly understood compared to Jupiter and Saturn, because no dedicated mission has visited them since Voyager 2's flybys in the 1980s. Webb has already revealed surprising atmospheric activity on Uranus, including bright cloud features and a faint ring system that were barely detectable from the ground. Neptune's Great Dark Spot, a storm system analogous to Jupiter's Great Red Spot but far less stable, may be observed over time to track its evolution and eventual disappearance. There are also plans to observe more icy moons. Europa in particular is a high priority target as NASA's Europa Clipper mission, launched in late 2024, approaches the Jovian system and begins its detailed investigation of the moon's ice shell and potential ocean. On the exoplanet front, the next few cycles will push atmospheric characterization into new territory. The TRAPPIST-1 system remains a crown jewel, with dedicated programs aimed at detecting or ruling out atmospheres on the habitable zone planets, TRAPPIST-1E, F and G. These observations require multiple transits to build up signal, because the planets are small and the atmospheric features are subtle. Each transit adds a little more data to the stack, like adding brushstrokes to a painting that only becomes recognizable after dozens of passes. The K218b follow-up observations, designed to confirm or refute the tentative DMS detection, are among the most anticipated results in the entire exoplanet community. If DMS is confirmed with higher statistical significance, it will not prove life exists on K2-18b, but it will ignite a firestorm of theoretical work aimed at determining whether any abiotic process could plausibly produce it. If it disappears, the community will sigh, recalibrate, and move on to the next candidate. Deeper into the cosmos, Webb will continue its survey of the high redshift universe, pushing to find galaxies at even greater distances and earlier epochs. The current record of redshift 14.32 is almost certainly not the limit. Theoretical models predict that the first stars could have formed as early as redshift 20 or beyond, and while detecting individual galaxies at those distances is extraordinarily challenging, gravitational lensing by foreground clusters could amplify their light enough for Webb to catch. Several lensing cluster programs are scheduled specifically to hunt for these ultra-distant objects, using some of the most massive galaxy clusters in the sky as natural telescopes. Historians still argue whether the decadal survey process, the once-a-decade exercise in which the astronomical community collectively prioritizes its scientific goals and recommends flagship missions, is the best way to allocate the enormous resources required for space telescopes, or whether it is a political compromise that inevitably favours the loudest voices. Regardless, the most recent Decayal survey, published in 2021, recommended a new flagship mission called the Habitable Worlds Observatory, or HWO, as the successor to Webb and the next great leap in exoplanet science. HWO would be a large optical and ultraviolet space telescope, equipped with a coronagraph capable of directly imaging Earth-like planets around Sun-like stars and analysing their atmospheres for biosignatures. It would do what Webb cannot: take actual photographs of rocky planets in habitable zones, rather than relying on the indirect transit method. The timeline is long. HWO is not expected to launch before the early 2040s at the soonest, and if Webb's development history is any guide, that date could slip. But the concept is approved, the science case is compelling, and Webb's discoveries are providing much of the motivation. Here's the quirky and somewhat melancholy detail about the future of space telescopes. Webb will never be serviced. Unlike Hubble, which was visited 5 times by shuttle astronauts who replaced instruments, fixed gyroscopes, and installed corrective optics, Webb sits too far from Earth for any crude repair mission with current technology. If a critical component fails, a key instrument, a reaction wheel, a communications antenna, there is no fix. The telescope will degrade gradually over the years, losing sensitivity as its detectors accumulate radiation damage, and eventually its fuel will be exhausted and it will drift away from L2 into a heliocentric orbit, silent and golden, a monument to what humanity could see when it decided to look. Some engineers have discussed the theoretical possibility of robotic servicing missions using autonomous spacecraft to dock with Webb and refuel or repair it. NASA has even funded preliminary studies, but no such mission is currently planned, and the technical challenges are formidable. For now, though, Webb is healthy. Its instruments are performing at or above specifications, and the data pipeline is full. Every week, new observations are downloaded, calibrated, and distributed to research teams around the world. Every month, new papers appear, some confirming previous findings, some challenging them, all adding to the growing portrait of a universe that is stranger, older feeling, and more richly detailed than any previous generation of telescopes could reveal. The golden eye is open, and it has no intention of blinking. You are nearing the end of this journey now, and the telescope is still out there, still staring, still collecting photons that left their sources before your planet existed. There is something deeply reassuring about that constancy. While you sleep, while you work, while you forget that the universe is vast and weird and full of questions, Webb remembers. It keeps watching. And what it finds next might be the thing that finally answers one of the oldest questions humanity has ever asked. Or it might be the thing that makes the question even more beautiful. So here you are. You have travelled from a launch pad in the tropical humidity of French Guiana to the frozen edge of observable time, and you have done it without leaving whatever comfortable surface is currently holding you. That is the strange magic of a telescope like Webb. It lets you be in two places at once, lying safe in your room and simultaneously standing at the boundary of the known universe, squinting at smudges of light that carry messages from an era no human was alive to witness. The journey tonight has covered a lot of ground, or rather, a lot of space-time, and before you drift off, it is worth pulling the threads together to see what pattern they form. The pattern is this: the universe is not what we thought it was. Not dramatically, catastrophically different. The Big Bang still holds, gravity still works, light still travels at the same stubborn speed it always has. But in the details, in the margins where the predictions meet the data, the cosmos keeps surprising us. Galaxies formed faster than our models allowed. Black holes grew to monstrous sizes before the universe had time to feed them through conventional channels. The expansion rate measured nearby does not match the expansion rate inferred from the infant universe. Dark matter bends light more aggressively in some places than simulations predict. Stars ignited earlier than expected, cooked heavy elements faster than anticipated, and died in patterns more complex than previous telescopes could resolve. And on at least one alien world, a molecule that on Earth is produced only by living organisms may be floating in a hydrogen-rich atmosphere above a global ocean, waiting for a follow-up observation to either confirm or deny its existence. Each of these findings alone would be a landmark. Together they form something larger, a portrait of a universe that is more dynamic, more precocious, and more fertile than the cautious models of the late 20th century dared to predict. Lambda CDM, the standard model that has guided cosmology for over 2 decades, is not broken. But it is being stretched, tested, and in some places gently corrected by a telescope that sees deeper and more clearly than anything that came before. The corrections may end up being minor, tweaks to parameters, updated assumptions about star formation efficiency, revised initial conditions, or they may end up being profound, new physics in the dark sector, modifications to inflation, a rethinking of how the first structures in the universe emerged from the quantum fluctuations of the Big Bang. Nobody knows yet. And that uncertainty, far from being a failure, is the whole point. Science does not progress by confirming what you already believe. It progresses by finding the places where your beliefs do not match reality, and then having the honesty to update them. Webb is the most powerful belief-testing machine ever built. It does not care about theoretical elegance or professional reputations or the sunk costs of decades of modelling. It just collects photons and reports what it sees. The interpretation is up to the humans, and the humans are doing what humans do, arguing, publishing, revising, occasionally panicking, and slowly, collectively converging on a better understanding of the cosmos they inhabit. Remember that grain of sand from the first deep field image? The tiny patch of sky that turned out to contain thousands of galaxies stretching back to the dawn of time. That image was not just a photograph. It was a philosophical statement. It said, "You're small and the universe is vast, and the distance between those two facts is not a reason for despair, but a reason for wonder." Every galaxy in that image has its own history, its own stars, its own planets, its own chemistry. Some of those galaxies are colliding right now. Some are forming stars, some are dying. And somewhere in that unimaginable web of light and matter, there may be another consciousness looking out into the dark and wondering, just as you are, whether anyone else is there. Historians still argue whether the search for extraterrestrial life is a scientific endeavour or a deeply human need dressed up in the language of chemistry and spectroscopy. It is probably both. The molecules do not care while you're looking for them. But the fact that you are looking, that a species on a small rocky planet around an unremarkable yellow star built a golden mirror and flung it 1,000,000 miles into the void just to ask the question, says something about what you are. You are the universe's way of looking at itself. That is not a new observation. Carl Sagan said something similar decades ago, but Webb has given it new weight, because now the looking is deeper and sharper than it has ever been, and the answers are starting to arrive. Here is one final quirky detail to carry with you into sleep. The gold coating on Webb's mirror segments is about 1,000 atoms thick. If you gathered all the gold on the entire telescope and melted it down, you would have enough to make a single marble. That is all. A marble's worth of gold spread impossibly thin across 18 hexagonal segments is what stands between you and ignorance of the first galaxies, the first stars, and the first light of the cosmos. A marble. The universe surrendered some of its deepest secrets to a marble's worth of gold and a few decades of human stubbornness. That might be the most hopeful fact in all of astronomy. And now you have reached the place where the story softens and the universe gets quiet. You've been holding a lot of information tonight, billions of light years of it, billions of years of it, and your mind has done well to carry it this far. But the weight of the cosmos is not something you need to hold while you sleep. You can set it down. The galaxies will still be there in the morning. The black holes will still be feeding. The plumes of Enceladus will still be erupting into the silence of Saturn's orbit. And Webb will still be staring, patient and golden, collecting the light that has been travelling since before your world was made. So let your breathing slow now. Let the numbers fade, the redshifts, the distances, the masses and magnifications. Let them dissolve into the soft hum of whatever background sound is keeping you company. The universe is vast and strange and full of unanswered questions, and that is not a burden. That is a lullaby. Because the questions mean there is still more to discover, and discovery is the gentlest kind of adventure, one you can have without ever leaving your bed. The golden mirror is watching the sky for you. The photons are arriving one by one, like slow, quiet footsteps crossing an ancient floor. And somewhere out there, at the edge of everything, the first light of the first star is still falling toward you, patient and unhurried, carrying a story that began before time had a name. Let it come. Let it find you here, warm and safe and wonderfully small, drifting off beneath a universe that has never once stopped shining.